Good morning or good afternoon, everyone, depending on where you are.
Hello and good afternoon.
Arthur, if you can hear me, give us all actually the interactive rights. Nice.
I can hear you, Pieros. Hello, everyone. Kalispera, dobry dzień, nihama. Oyo gozaimasu. I don't know what time it is in Japan. Howdy. Hello, Leonard.
GNU Radio would be my favorite. KiCad as well. KiCad.
You have to print it over there. KiCad is appearing, I think. Yeah. Who put Outlook?
Outlook.
That was me. That was me.
What's a good one?
Oh,
what's the circuit simulator? Firefox, seriously?
Cooks, no?
What's the circuit simulator? It's Q-circuit or something like that?
Cooks.
Cooks?
Yeah, C-U, how do you spell that? C-U-C...
ING Spice.
Fabian, no.
C-U-I-C? Oh, yeah. Yeah.
Chipmunk diglog. Anyone used that in the past?
If you're gonna put Firefox in there, I think you should put Git.
If you want, you can put it. Yeah.
My favorite one is.
I think I could not live without VI. I'm even VIing PDF files. That's a fascist story. A good one, Konstantinos.
Well, Anaconda is not exactly an open source tool. It's just a distribution.
No, it's Linux. That's a tool in the end.
sklearn. Who does any machine learning?
Yeah, we do. Arthur, can I take presenter role for a second?
Yeah, you can take over. And to everyone, this is the connection test part. So you're welcome to switch on your
Microphone.
webcam, microphone, until for the next, what is it? 10 minutes, 9 minutes, and then we start.
Eric, I have to put your screen, your video full screen. You have an amazing background.
Good morning.
Crazy. Good morning. Wow, oscilloscopes and everything.
Good morning, everybody.
Hello, boys.
That's the hem shack.
Good morning, everybody.
Hello, Zabi.
Hello.
You get the message?
Yeah.
Okay.
What time is my talk? It's 2:30, right?
So it's yesterday. I don't know, with the 2:30, right? Yeah.
Yeah, so your answer about the afternoon, it's 4:52 a.m. here. I'm on Pacific Standard Time.
Oh, all right. Yeah.
All right.
I know that all of you are old pros, so for somebody that's just a newbie like me, is there a getting started, like, what do you recommend for somebody that to look at just to get started?
Vim tutor. Love it. Get starting in what, Leonard?
Well, yeah, for the satellite comms or either like Sagnos or something like that. You know, just to establish a link between something.
Yeah. Radio link.
Yeah, on Sagnos, I would suggest checking out on how to build a non-rotator ground station, which is pretty simple and really easy to set up. That would probably be an easy way to get started. But in general, even without having a satellite ground station, it depends on what you are used to do. For example, there are people that have no ground stations, but they are really comfortable using Tai, if I pronounce it right, to parse satellite data. So it depends.
Yeah, your audio was muted. I mean, I have I suppose, yeah, establish a ground station I think would be good. Antennas and stuff like that. I have a Pluto SDR, 2 of them. Who's using a Pluto SDR, by the way? Anybody? No.
I am using my Q100 station.
Boris, you're using it on your station, on your ground station?
Yes.
Oh, awesome.
Adelon Pluto?
Yep.
Yeah. Are you using it just directly out of the box, or have you modified it?
You need to modify it. It's the durability of the frequency, the stability is not good enough to work with some, how can I say, FSK kind of demodulations. You have to modify it. But I was using Etis Research UHD. It's when you compare the prices, it's unbelievable. So just a crystal modification makes it perfect.
So you're just putting in your own crystal or clock oscillator source?
There are many options. The first one is you can buy a new crystal which has less ppm. For $3, you can use a stable 10 megahertz or 40 megahertz reference oscillator, or you can use a GPS DO for stability. It's from $3 to, let's say, $100.
Yeah. Yeah, there's a depends on your cost constraints.
Darish, can you move your webcam and we can have a tour through your hackerspace?
Yeah, you have some kind of a hackerspace behind.
You see, here is the modification, and this is the external reference input if you need it. Otherwise, I have a modified Excel there. I don't know if it's usable or not.
Yeah. Have you done any VHDL modifications or Verilog?
Yeah, I'm trying to build my own SDR solution or my own transceiver solution on the top of this. And I'm following a French guy who is doing ATV with this and using his FPGA software on it.
Yeah, that I was gonna try to do more or less the same as well. Have my own front end. GNU Radio actually has a I think I saw a tutorial on where somebody showed the difference in performance between putting some of it in the hardware and some of it just,
Yeah, but it's only $100. Sorry, it was $100. I think now it's $150. But for $100, it's an unbelievable transceiver.
No, I agree. Yeah, I mean that's why I picked it. Did you see my controller that I did yesterday?
Who talked? Oh, nice colors. All right, 2 minutes to go. No.
So
Do you still need to upload the presentations out, or are you right?
There's someone that didn't finish his presentation. That might be a limiting factor.
Who's been talking right now? You mean? Or some...
Probably the one that is presenting first in this room. One, that's a new record. Congratulations, dude.
I hear
you don't
room,
know me.
I hear room 2 is a cool room.
Nice head. Hey Samuel, good morning or evening, or I don't know where you stand.
Good night.
Good night.
It's 9 p.m. here.
9 p.m. Where are you?
Southeast Asia, Singapore.
Hey Sam, nice to meet you.
Almost.
Hello, nice to meet you.
Nice to meet you too.
Looking forward to everyone's talks later.
Yes.
Very cool.
They need better drawing tools for this.
All right. Just start my majordomo file. Amazing. All right, people, we should start. So. Okay, let's kick off. Hello, everyone. People of the open source CubeSat workshop. Welcome back from yesterday, or welcome if you just joined. That's amazing. Just a short reminder, the open source CubeSat workshop is a community-built workshop. It's for people building space the open source way and sharing knowledge. Good, you have your drinks. Me too, I have to fill that up though. But good. Yeah, you have to keep your drinks. The presentations are going to be very interesting. You won't be able to have a bio break until the real break. All right. So, so take it easy. We'll have room 1 and room 2, but we'll soon get to that today. But on the next slide, yeah, you did something else, or you wanted to do something? You have to scream. So yesterday you screamed your favorite open source project. Maybe today you have to do something else. I don't know what, but let's imagine. What do you want to scream about? I see. So I didn't hear you, Boris. You are muted. Okay, scream
My favorite satellite mission.
Anything
anyway.
Yeah, that's a good one. Favorite satellite mission, and then we go with favorite SatNox mission. So okay, warm up. Please shoot in 5.
Wait.
Oh, wait, what?
Needs to be satellite, or it can be deep space probe or something.
As you want.
Good point. Spacecraft, anything.
Spacecraft, okay.
Spacecraft.
Because it's different thing, yeah?
Yeah.
Okay.
Good point.
Okay, I won't stop anymore. In 5, 4, your favorite spacecraft. 2, 1, now!
Yeah.
Oh, Boris, that was not screaming. Maybe you have people sleeping around you. Okay, then once again, you know your mission now. So from here, inhale. Once again, 5, 4, 3, 2, favorite mission now! Good. We reached saturation. That's good. Just a quick test of the pooling facility that we have here. I would ask one question. Could you hear everybody? So, oh, sorry. Once again, could you hear everybody? I see. Yeah, it's so good. Once more, 70%, and we're for go. Yes, look at this. Yes, you could. That's good. So this is pooling you can use during presentations, and but you have to speak up the question. All right. So next, a little bit of logistic with Pieros. If you may, Pieros, I can still present if you need.
Cool. So logistics, pretty much the same like yesterday, and we still have 2 rooms, and this first session of the day will be split in 2 different rooms. And there is always a lounge that you can visit and just hang out there. It's always open. By the way, for the rooms today, we do have also live streaming going on. Those are different links from yesterday's on YouTube, but you can find them on the channels and on the OSCW page. Recording is always happening on both rooms, whatever is happening. So we will be uploading everything after the sessions are finished and the conference is finished, and then we'll have time to edit, hopefully, and do the uploads as soon as possible. And as always, we do have the 2 chat channels. One which is thank you for the links. Here you can find the links on the OSCW page. And the chat channels are on Element, like yesterday, but also you can post your questions here on the big blue button or on the YouTube channels. We will be monitoring all 3 different options for you, and we'll make sure to forward those questions or comments. So that's for the logistics. Once again, the bathrooms are still at your home, so no change on that.
About the access keys?
Oh, yeah.
Yeah, so I didn't mention anything about access keys because there are none anymore.
Yeah.
So just, we figured that since it worked really well in terms of the big blue button installation yesterday, like we opened up basically the access to both rooms. So feel free to join those directly, and let's see how this goes. Hopefully we're not going to crash the place.
Arthur? Well, session-wise, okay, those are the ones from yesterday, but the procedure is the same. You have you go to the timetable, you see the sessions that are ongoing, the room, and which talks are being given. You find this all on the Indico website.
And share the link again in case you want directly to jump to Sunday today. All right, so we're on room 1. You can feel free to choose your room now. This is the time for that. So just maybe we can mention room 1. We have talks managed by Pieros and Arthur, and this will start with Juan Lu on TLEs and OMMs, and on room 2, this is Metasat, the project, metadata for small sat missions. And you can that will be the first talks over there. Give you a little bit of time.
You watch room 2?
Room 2, yeah, maybe.
Then I think it's a good time if we go now into the rooms and make sure we upload the presentations.
Yeah.
Right?
Yeah.
Probably, yeah.
I still have 2 minutes.
The upload also takes a bit.
All right. I will move to room 2.
Juan, you can post the links on Reddit for PPP, and then PPP crashes, and then that buys you more time.
It's a good idea, actually, but I don't have time for it.
Hello.
Hello.
We are on room 2. So
What's happening? We're getting room 2.
In 2 rooms at the same time.
You have to switch off your microphone here, Elif.
Cool.
Good. Yeah, Juan Luis, no stress. We're waiting for you.
He'll make it on time.
Well, I can start with his introduction, and I can make it a really, really long one, like going through all the different papers, different projects, and
from his birthplace, maybe you can.
Of course. Even before that, like his lineage and ancestors,
how it all started. Centuries
also,
ago.
to maybe increase the pressure a bit, I suggest everyone switching off the webcam so that Juan Luis is the only one in the focus.
Unfortunately, I have to stay on. I'm giving the intro. Don't worry, Juan. Like I can buy you some time here.
Room 2 has started. Awesome.
Do you want me to go next, Juan?
I'm ready. I still have 0 seconds. Okay, exporting.
Exporting. And now uploading.
Good. Can I take presenter? Yes.
Take all the presenter you want.
All right, good luck, Juan Lu. Cheers to you.
Let me know when you're ready. I'll start the intro.
It's uploading.
Here I can see it.
Yeah, room 2 is already going. I mean, what's up with that?
So Juan, you're good?
Go ahead.
Okay, so for the first talk of this session, we have Juan Lu. And Juan Luis is an aeronautical engineer from Spain, working as a mission planning and execution engineer at Satellogic, a satellite imaging.
Astrophysics. And really where those two things overlap, in my opinion, is in helping
We get some
another
echo
scientist
from
with the CFA.
Leonard. So Leonard, if you can please, mute. Thanks. So starting again. Juan Luis is an aeronautical engineer from Spain working as a mission planning and execution engineer at Satellogic, a satellite imagery company. He has been contributing to the scientific Python ecosystem for almost 10 years, and he is the author of many open source packages, including Polyastro, a Python library for interactive astrodynamics. He is also professor of Python for data science in several different business schools and a freelance consultant for R&D projects in the aerospace industry. And for today's talk, are you really tired of squinting at punched cards to find out about the orbit of your satellite? I know I am. So pay attention to this talk and find out everything about how the future works for orbits.
Thank you very much, Pieros. So hello, everyone. I'm super happy to be here. Thanks to the organizer for this wonderful event that is working so well. So today we're going to talk a little bit about the past and the present and how the future should look like. So the outline of the talk is like this. So we're going to describe a little bit what is a TLE exactly, and more specifically, what is not a TLE. We're going to discuss a little bit what problems do TLEs have, and why should we stop using them as soon as possible now that we have alternatives. We're going to talk a little bit about what's the new proposed format, so OMMs, orbit mean element messages. Some details to consider though, based on my very short experience investigating this format and some of its current shortcomings. And then we're going to go over some findings that we were researching into what's the current status of OMM support in the open source ecosystem, which is part of work that we're doing for the OpenSatCom initiative. And then we will go to the conclusions and Q&A. So I hope that you have lots of questions about this one. And so what's a TLE in the first place? Well, this is a contested question. I ran a poll on Twitter before doing this talk, and this was by far my favorite answer. So a zombie data encoding system dating back to the punched card days with an amazing year 2056 problems, among other issues. So definitely this was my favorite response. A good summary, but not very insightful though. There has been people all around the world confused by TLEs, and in fact you can see this excerpt from one interview to one of the presidential candidates of the US elections. This is 100% real, of course. And this was the face of the interviewer when seeing a TLE. So as you can imagine, this is pretty confusing already. So what you have in front of you right now looks like a TLE, but it's not. And I want to give you a very important warning here. This TLE stands for two-line element, and what I'm showing on screen has 3 lines. So first of all, we have to get the arithmetic right. So what we have here is a 3LE and not a TLE. But anyway, despite this nitpick about the format, a TLE is a representation of the orbit that is very compact, that has both a representation of the mean elements of the orbit as well as some extra numerical information that's used to understand how the orbit changes with time. And it's usually a product of a set of observations, as we're going to see next. So in the words of the author of Selstrack, TLEs or two-line element sets are a way that the US government uses to provide general perturbations orbital data. Okay, and what does this general perturbations part mean? So very short and very quickly, what this means is that the osculating orbit that would be described by the two-body problem and the equations that Kepler and Newton discovered centuries ago is never the actual path that the satellites take in orbit. And in fact, there are a lot of perturbations that have an effect over this orbit, which are summarized in lots of different textbooks that you can find. This is a screenshot from my favorite one, Vallado. And there are several effects like the non-sphericity of the Earth, the atmospheric drag, higher order terms of the gravitational field, and thermal effects from the moon, solar radiation pressure, the tides, and so forth. So we need some sort of way to compress all this orbital information and understand how can we propagate this orbital information into the future. And that's what TLEs are. So far, and as I was saying, these general perturbations orbital data are generated by fitting a set of observations. And in the case of TLEs, they're distributed through Celestrak and other public channels that we will mention later on. This orbit information is generated by observations from the 18th Space Control Squadron, which is part of the US Air Force. So it's some sort of public service that the US Army does for the rest of the world. And as I was saying, these elements are distributed in several places, and arguably the most popular of them is Celestrak, which is this one that you have in front of you. And this one distributes TLEs in an open way, so you don't even need a registration for it. And they're tracking most of the visible satellites, if not all of them, as well as debris, objects, and so forth. Okay, so that was about TLEs. So what problems do TLEs have, and why should we stop using them? And the answer is that they have quite a few. And so the first one is that by the very limitation of the format of the TLEs, there are some numerical errors that are introduced because of the limitation in decimal places that are used for the quantities. So for example, this is again an excerpt from Fundamentals of Astrodynamics and Techniques, which is a very good book that I recommend you to check it out. So as it's said here, by the limitation of the decimal places that they use for the angles, there's an error introduced for LEO, so low Earth orbit satellites, of about 6 meters, and for geosynchronous orbit, about 35 meters. Of course, this is very small compared to other measurement errors and the fitting error of the TLE itself and so forth. But for precise orbit determination, this is not acceptable by any standards. And also, why use a format that already imposed this kind of numerical error, while we don't have anymore this space limitations and bandwidth limitations and so forth. But then the other one is that, which is also related to the limitation in decimal places, there are two things here that have a very big problem. One of them is the year, which is this one that I'm highlighting here, these two characters here. And the other one is the satellite number, which is these 5 numbers that you can see here. So about the year, as you can imagine, having only 2 characters must have been very fun in the year 2000. And the decision that they took is that for years, for pairs of digits that are less than 57, we assume that it's in the year 2000. So for example, if we see here 01, that would be for the year 2001. But for pairs of digits that are above 57, then we assume that we're talking about the 19s. So in this case, as you can see here, this old TLE has the digits 86, and therefore this corresponds to 1986. And this has an obvious problem because when we arrive to year 2057, we will not be able to use this representation anymore without making some sort of adjustment. And then again, this NORAD catalog number, which is these 5 numbers here, again, has an obvious limitations because when we pass the mark of 100,000 objects being tracked by the Department of Defense, we will not be able again to use this sort of representation. You will think that this mark is sort of far away into the future, but the truth is that thanks to some improvements that the US has been doing in tracking both of satellites and of debris objects, they're increasing the size of the catalog pretty quickly. So it's very likely that we're about to reach this limitation. And besides, they found an alternative solution in this case, which is introducing what they call an alpha 5 numbering scheme, which probably means that they're going to introduce letters as well as numbers to increase the number of objects that can be tracked by the system. But again, this is just a workaround for a format that is already too old, that has numerical limitations, and that is too difficult for humans to read. So with all these things, what is the new proposed format? So OMMs. So let's talk a little bit about it. OMMs are the bright future, and in fact, they're not so new. This new format has been around for already some years, and we're going to discuss about this right next. But in May 2020, so just a few months ago, Celestrak, the website that publishes all the TLEs, announced that they're going to switch to this new OMM format to distribute this general perturbation orbital data. They're going to keep both for backwards compatibility purposes and not to break everyone's software, because we know that these things take some time, but they're still encouraging everybody to use these new formats. So again, these OMMs were standardized by the CCSDS, which is the standardization body that we all know and love. And to give you a brief, to give you a quick overview of where they stand in the hierarchy of formats standardized by CCSDS, Orbit mean elements messages, OMMs, are part of the Orbit data messages, which also comprise other two formats, Orbit parameter messages and Orbit ephemeris messages. And they're all part of navigation data messages, which also include attitude data messages and tracking data messages. So we're at the moment focused on this part over here. This is how they look like. So instead of having this compressed format with character limit for all the fields, we can have this sort of representation that includes the name of the keywords.
1 minute left.
Thank you. So like eccentricity, mean motion, and all the rest of mean elements. And also some metadata like what's the name, who was the producer, and so forth. Here I took a couple of screenshots from Celestrak of how to obtain this kind of format, and you see that you can get this both in JSON and in XML. I'm going to mention this very quickly because I'm already about out of time, but the interesting thing about the standard is that only XML and an ASCII format are actually standardized. The JSON format was not standardized anywhere, so it's just a translation that we do from the name of the keywords that appear in the standard. And also this XML format is not exactly in the standard that defines the OMMs, but it's in another one. Okay, so I'm going to skip that. And about the OMM support in the open source ecosystem, my one-line summary would be that it could be better, but also could be worse. We're about to publish these findings as part of the OpenSatCom initiative, but I can give you the summary already. So we surveyed several open source libraries, Python SGP4, ORCID, and then some others that are not so well known. And I found like only one library that can read both key value notation and XML, which are the two notations standardized. And then the rest have some mixed support for all the rest of the formats. This one here was discovered like 1 week after I finished the report, so I'm going to add this as an extra. And in general, I think it's quite limiting that we don't have like a good way to support these formats in well-known libraries like Python SGP4, and also that we don't have two-way conversion between TLEs and OMMs, unfortunately. So in conclusion, it's already time to switch away from TLEs, but the support for the format in the open source ecosystem is not so widespread as I would like, at least. A two-way conversion between the old and the new format seems to be missing from what I understand. And also that XML is kind of, yeah, sorry. So, and also that XML is a little bit contested because some keywords that appear to be mandatory cannot be filled with total accuracy from the producers. So thank you very much for your attention, and I'll be happy to hear your questions.
Thank you, Juan. Let's see what questions do we have on the channels.
So Leonard Diegas, he's asking, do you want to use the mic, or I read the question? There's the limit to 100,000 objects. I think you partially answered that. How many Starlink sets are going up?
I don't remember the last number. I think they count by the tens of thousands in their plans, like the last filings that they did for the Federal Communication Commission, but I'm not 100% sure about this. And also, like, this is an aspiration, of course, it's not the current reality. But they already have a few hundred of them, right? I lost count, to be honest.
Yeah, so the TLEs, I mean, the question really was kind of a, sarcastic. It's the 100,000. We're going to blow through that very, if we haven't already, real quickly with Starlink, because their plans for their system is like 60,000 or something like that. So
okay.
Or more. And remember, those are kind of disposable. I think they're just their mission is just a few years. They come back down, they send another one up, and so they're going to blow through the numbering scheme really quick.
Do we have another question? Jan Maas is asking about the numerical accuracy in the OMM. Please,
Yes.
Close the webcam. Thanks.
It's a good question. In principle, OMM and TLE are just formats to represent general perturbation data, and therefore they have like the same accuracy, or to be better put, the propagations have the same accuracy because they are supposed to be propagated with the same algorithm, which is called SGP4. What I mentioned at the beginning is that as TLEs have a limitation in how many decimal places they store, they already introduce some numerical differences just by the way they store the data, but still they are much smaller than the propagation errors anyway. So
we have a question from YouTube. Jan is asking, first off, he says, great talk, and what would be the best place to find information around the new format? I suppose the standard itself, right? But also regarding the adoption?
Well, regarding the adoption, I hope that the report that we're about to publish would be the best way to look at it. I hope. And also that I hope that it can be a living document, right? That we can like improve it as long as there are more libraries supporting it. And regarding the format itself, yes, I agree that the standard is not super hard to read. Like it's a normal document after all. It's long, but it contains all the information firsthand, so I would recommend you to go there. It's publicly available, you don't need to pay it.
And we have another question about why isn't there a single way to load OMMs in Python, and why the effort seems to be spread among different libraries?
It's a good question, and I was wondering the same thing while doing the report. I'm not sure about why. I think, the library that everybody or most people are using to propagate TLEs, which is Python SGP4, Brandon Rhodes, his author, wants to maintain it as simple as possible, and in particular, he doesn't want or is not very interested in supporting XML, and I can totally understand the reasons. And there has been some effort like to add import functions and export functions, but I think the community hasn't realized that we really need to move away from TLEs until the sales track announcement from May this year, which was like, what, 6 months ago? So I think it's just a question of time. Like when we start feeling the pressure, we will get to it and maybe create the one single library we should use to convert to and from TLEs and OMMs.
And I think a final question, if we have time, what is the max number of satellites that the new format supports?
In principle, I don't think there are any limitations in that because it's not constrained by the number of characters, so it should be unbounded, I think.
Cool. And quickly, a final one, is there a tutorial for using and forming OMMs, or just we have to rely on the standard?
You know, for using OMMs, it's as simple as loading them with your library of choice. Refer to my previous slide where I was showing which libraries you can use. And then they are propagated in the same way as TLEs, and they produce a Cartesian result in the true equator mean equinox frame like it was before. And about forming the OMMs, I think that standard itself would be, again, the primary guide, and I don't think there's a tutorial out of it. But maybe we could produce one as well. Who knows?
Cool. And I think that would be all for this talk. Thanks a lot, Juan. That was super interesting, and I think that the conversation can also continue on the later in the day when we have some breaks and everything. People are still interested around this a lot. And for our next talk, we're going to be going to Xavi, and Xavi, known as Crespum also, or online. Welcome, Xavi. He is an LSF core contributor, an open source enthusiast, an embedded system engineer, and a phenomenal project leader for Polaris. So this talk is going to be about Polaris, which is a machine learning project for exploring and analyzing telemetry data from the SatNOX network, but also beyond that. And for this specific talk, it seems that this is the first time that the team has used Polaris not on telemetry beacons, but rather on real science data. And certainly you won't be disappointed by the results. So, Xavi, take it away.
Hi. Thanks, Polaris. First of all, thanks for setting this conference up in this hard year. So thanks to the organizers, thanks to also to LibreSpace, of course. And well, I wish I could see you live, but it's what it is. Hopefully next year or the year after we will finally meet in person. So today I'm going to talk a bit about Polaris. I'm going to show you a use case study of some science data from Bobcat 1 satellite, cubesat. I'm not a member of Bobcat team, so yeah, excuse me if I make some mistakes because I'm not part of the mission. So yeah, this is just a case study of how to use Polaris, not on SatNOX data because science data is not on SatNOX, but rather on science data that the team gave us for the analysis. So yeah, hopefully I can make this work. Yeah. So first of all, a little bit of background about Bobcat satellite. Bobcat is a satellite, a 3U CubeSat, the one you see in the picture. It was made by the Ohio University, that's in Athens, but not Greece, Ohio, the USA. It was launched on October the 2nd in an Antares rocket, and it went to the ISS, to the International Space Station, and from there it was launched, if I'm not mistaken, through or with nanoracks on November the 4th. The mission goals, of course, as pretty much any satellite that comes from a university, it has some education and outreach goals. So you can imagine it's a real hands-on experience for students. In terms of outreach, it's really important because, satellites get a lot of attention. So it's a good opportunity to be part of this kind of teams. But also this satellite, it had a scientific goal which hopefully there is someone from the team, because well, as I said, I'm not part of the team and I don't fully understand the goal, but the goal is basically that you can measure GNSS interconstellation timing offsets. They carry a payload with GNSS receivers. Well, actually, I think it's one receiver that can get data from many GNSS satellites or constellations. And because of the position, they can measure timing offsets, and this is very helpful for giving more accurate measurements about the other orbits. But yeah, the specific goal is not important for Polaris, but yeah, it's just for you to understand the context a little bit. And also, Bobcat it's really integrated into SatNox. So far, it has, I think, 5,000 or so telemetry frames decoded, and you can also access the dashboard. It's going to be a bit hard. I don't know how to do that, but I will send you the presentation later. But if you click here, you will go through the SatNox dashboard, where you can get the telemetry, the decoded telemetry. You can see the status of the satellite, and that's because the team they have made the decoder for that, or they have contributed with that to the SatNox project. And thanks to that, the team can also get telemetry from all over the world, thanks to also SatNox stations. So yeah, they've been benefiting from this. Someone published the link. My bad. But I think I cannot access here. I can. Let me try to show you. Can I show you? Do you see my? This is not the screen. Do you see my?
Yep. We see the screen with other things though. But yeah, fantastic.
This is the screen, right? All right. So this is the dashboard. You can see this is the This is the logo of the mission. You see the frames count. The last frame was received 3 hours ago. The battery status and the historic data of this is solar power, solar panel power or battery. Well, you can, thanks to SatNox, they have this information not only when the CubeSat is over Ohio, but also when it's over any of the stations of SatNox. And well, you can scroll more and more, and you have a lot of these parameters. But in this case, I'm going to tell you something about Polaris now. But the difference is that last year we were showing. Last year we used Polaris with SatNox data, and that's with beacon data that everyone can access for, let's say, for free, but thanks to SatNox, of course. But this year, instead of using that data, we are using science data specific from the satellite, and that's really that's really helpful, because this data is not public on SatNox. It's private for this analysis. Hopefully, it will be open data soon. But this is not the same as accessing this telemetry that I have just shown you. So this year, Polaris, we've made a lot of effort. We are now part of the LibreSpace Foundation. We are one of the projects of the LibreSpace, and we are collaborating on many other aspects. Of course, it's also important that we participated again of the Google Summer of Code. We had one wonderful student, Aditya, which I'm not sure if he's here, but thanks. You will see what he's doing in a few secs. As part of the Google Summer of Code, we have integrated space weather for the analysis, and we're also working, this is not done yet, but we're also working on behavior analysis of time series. And well, of course, we support many satellites. like so 2, Cubic 1, Bobcat 1, and in fact we don't need a decoder, so in fact we support all of them. But these are the ones that we have used in the past. So I'm going to skip fast because I want to show you the demo and not the details of how Polaris works. But overall, this is the same like last year. We fetch data from SatNox. We learn. This is the machine learning part. And then there is a way to visualize the data, which is just for now for the dependencies. We have a dependency graph that I will show you in a bit, and then we're also working on the anomaly detection, as I told you. But this is not ready yet. And regarding the fetch part, this is new also this year. It's actually here and here. We fetch space weather data and we merge that with the data from SatNox, and that gives us some more context. And well, also this is just details, but we are Polaris is written in Python, and thanks to that we are benefiting from the rich ecosystem. And these are just a few tools that we use that are available, that are open source and available to everyone. XGBoost and Fetch, MLflow, Research, or Scikit, or even AstroPy from Juanlu, who was in the talk before. We use all these tools, and thanks to open source and to the Python ecosystem. And I will show you, this is what the graph means, but I will show you in the real graph now. Let's go to the demo. For the demo, we had to use a big server. It's got 21 CPUs, 64 gigs of RAM and SSD, and in this GPU it took no GPU, of course, because this was a server from Ohio University, and it took 30 minutes here. And this included, this is not frames, but lines actually, and it's 441,000 lines. So it's missing a K here. And that's 172 megabytes. And each line contains a set of values that belong to the same timestamp. And that's space weather and science data. And regarding the science data, so the important is the carrier to noise ratio. And that's really important because the GNSS receiver, which is the main payload, that's what it uses. Then it has also, of course, gyroscopes and magnetometers, or even sun positions that you will see. And space weather data, you will see a lot of information in the graph, but it's basically daily geomagnetic data, daily solar data, daily practical data, and that's a lot of parameters that, to be honest, I don't really understand all of them. And yeah, so let's go to the demo. The demo you can access in this deepchaos.space website. I will share my screen now. You should see this now. Well, it's actually redirecting to another website, to polarisml.space, but yeah, it should be the same. So this is the graph that we've obtained. What we expected and what the team expected was this. Sorry, you can go around the website. You can search. You can, let's say we want to find the carrier to noise ratio. So as you can see, it's in the top left corner, and you press enter, and it will go through to the node. And as you can see here, carrier to noise ratio, you can also drag this node if it's easier for you to understand and to move it around. It's really linked to radio flags, and this is space weather.
30 seconds left.
Sorry?
You have to finish up.
All right. So it is fast. This is the carrier to noise ratio. It's really linked to radio flags and also to the sun sensor. And this is to be expected. This is what the team expected. The carrier to noise ratio is really it's really influenced by radio flux, by space weather, and also the sun sensor. It's also really linked to carrier to noise ratio and to space weather, of course. So this is the main what they were expecting and what we saw in the data. This links just mean the data is really linked. And also, if you see these small dots, the speed, it means the faster, the more significant the relationship is. So let's say here, the significance of the links is it's higher. It's more important that the relationship between CNR and the sun sensor rather than CNR and space weather. And then, well, you can also see a bunch of this stuff, but you can play with it by yourself. This is the cluster of space weather. The radio flux it's linked to pretty much everything. You can also color if you want to know about the gyros and you want to know you want to locate them. You can press Control Enter, and you can color the gyros, and that will make you understand better if they are related to something or not. They should be related to temperature, but to be honest, only gyro Z is related to temperature. But yeah, it gave some interesting results, and this is only a part of the data because, as you saw, the results were well, it took a lot of computational time. So yeah, that's pretty much it. You can play with the graph by yourself. Visit the deepchaos.space. Yeah, thanks to the team, to Kevin and to Brian, and also to Polaris guys who helped me really much to make this possible. And now, if you have questions, I'm all yours.
Excellent. Thank you, Xavi, for that. And the first question would be, in the machine learning part, how are you generating the labeled data?
So the labeled data in the graph, it comes from when you retrieve data from SubNox. You just have some label in there. Sometimes we don't know. So for instance, you see a sun sensor. That's clear what it is, but you see sun something, and we don't know what it is, and we don't care because we don't perform the final analysis. But the satellite operator is the one who has to understand what it means.
Yep. If I can answer. So we don't actually predict. So we don't use the telemetry and labeled data as per supervised machine learning methods. We use a supervised machine learning methods on the data itself. So the data is the label. So I could stop here.
Okay, there was another question about the GNSS antenna sitting on the minus Y face, and apparently it is. There was a question about the Python code and where this is available, and we posted the link. That's on
yes.
Polaris group in GitLab under the LibreSpace Foundation repositories.
Yeah, you should have it on the screen now, I guess.
Yep. And posted the link. Any other questions? Anyone from the room?
Well, just join us. If you have questions, we also have a channel on Riot, and you can ask questions there. Or it's a very open community, so you can ask questions, and I ask them questions every day. So that's.
I'm going to ask a question. What's your plans for hosting this kind of graphs for different missions and automatically generating them alongside the dashboards that we have for the missions?
Well, that's an interesting question, and this study, let's say it was not easy because, as I said, we usually drink from SatNox, and this is not drinking from SatNox directly, so we need to do a bunch of adjustments. And I think we are going to have an interesting discussion about this next week, because we need to, as you said, to host this for different missions. And for different data, I don't know if we want to host it, but at least we want to make that possible and easy. So it's going to be an interesting talk indeed.
Cool.
And also, well, also because it requires a lot of power, computational power. So that's
We'll
also
find a solution for that.
Yeah.
Cool. So thanks, Xavier, for this really interesting talk and developments on Polaris. For our next talk, we do have Samuel with us to talk about Orbit M. Samuel Lowe is with us. Let me see if the screen is ready. The presentation is ready, and I think we also have him on the microphone, but not on screen. And now we have him on screen. Fantastic. Welcome, Samuel. So Samuel is a scientist in DSO National Laboratories, and he works on developing navigation algorithms for Singapore's first formation flying satellite mission. He also performs orbit design, simulation, and mission analysis. So today, he's going to talk to us about Orbit M that allows you to size up your mission lifetime with a click of a button. Sounds wonderful. So thanks for joining us, Samuel, and the floor is yours.
All right, thank you for accepting me for this workshop. So before I start, maybe I better thank the organizers. You guys have done a fantastic job. I've thoroughly enjoyed all of the presentations so far. And a special shout out to Juan Louis also, because he was the one who actually introduced me to OSCW like many months ago when I first chatted with him. So in the spirit of the open source CubeSat workshop, I'll be introducing to you guys the Orbit M, or Orbit Maintenance and Propulsion Sizing tool. And in this presentation, I really just want to touch on three main questions and how Orbit M can answer all of them. So the first question is, why should orbit maintenance analysis actually be fast? The second question is, how can it be much faster, especially with the way we are doing things right now? And finally, I'm going to run through what Orbit M offers and how you can actually use this software. So now when we are moving to this new space industry, we realize that a lot of satellites need very agile development. And that means that your requirements are changing all the time also. Especially if you're in your initial review stages, you often contemplate between different solar cell structures. If you're using a SAR satellite, then you'll be thinking about what kind of different reflectors you should use. Each time a new idea gets proposed, the area to mass ratio of the satellite changes. And then you have to run the whole orbit maintenance simulation all over again. Now, for in my company, where one of the issues that we had is we were very reliant on this using commercial software like STK. And so a lot of things can actually be sped up and simplified if we used our own, say, I wouldn't say proprietary, but at least our own way of doing things. So we found that things like the reflector changed like 2 or 3 times in the solar panel arrays. They were contemplating sometimes between looking at taking inspiration from Gossamer, which is like thin film solar array, so it's like soft materials, and also looking at how other companies like SpaceX does a more mechanical rigid deployer. So this one is probably heavier in mass. So with so many iterations, we decided that we have to, or rather I decided that I have to make the orbit maintenance analysis much faster. So before I actually run through how it works, this is like the typical workflow of how you set up an orbit maintenance simulation in STK or maybe GMAT. So there are a lot of objects. You make the scenario, you make the satellite, the astrogator parameters have to be set, and you have to set a whole bunch of routines in the GUI, and it was just really too much work, especially if you have 10 different iterations that you want to check the mission lifetime of, or possibly 10 different propulsion units that you want to test. So I decided, let's see if there is an easier way to make orbit maintenance analysis faster. So I'm going to hold everyone back. The math, like I was not expecting to put too much math in, but I thought I should put enough to let everyone understand. So how do we actually make it faster? Well, the key idea is that a lot of these commercial satellite propagation softwares, they propagate all 6 of your state vectors, and some do it with very high precision, which is good. But in lifetime simulation, actually your decay rate depends on how thick your atmosphere is, your atmospheric density and your drag effects. And so you don't actually need to compute all 6 of your state vectors in each iteration. You actually only need to compute your absolute scalar radial values. So starting from this, let's see if there's a way that we can actually make the drag computations a lot simpler. So if you look at the left box over here, this is just the total orbital energy that we've learned maybe in our first year physics. And from here, I want to derive 2 quantities, and I'll show you why these 2 quantities are important later. First, I will derive what is the rate of change at which energy changes with my radius, and finally, the rate of change at which energy changes with time. And the first parameter, the radial derivative, can be taken by just simply differentiating whatever you see on the left-hand side, the total orbital energy. The time derivative, we go back to first principles and we just look at how work done is defined, right? The rate of change of the energy is the force multiplied by this ds, is your infinitesimal movement in the direction of your motion, dotted with the direction of your force. And doing all of this, we realize that this time derivative simplifies to 3 main parameters. 1 is your drag force, 2 is the actual orbit radius, and 3 is actually your mean motion. And so let's put this together. So we've derived the radial derivative and we've derived the time derivative. And this very simplified model that I created simply just says that, okay, I don't need to compute my 6 orbital elements. I just need to compute what is the rate of change of my radius with respect to time, the radius of the satellite with respect to time. And if you just look at ignoring the math on the right-hand side first, this is with some calculus, it's just du over dr inverse. So it's actually dr over du dotted with du dt. And this gives us dr dt. With, in the interest of time, I won't touch too much on the derivation, but the final result is actually really, really simple. Oh, one important thing also, you need at least a fast way to compute your atmospheric density. So for orbit M, it uses a lookup table, so there's no need for any computation. It just looks up the atmospheric density, plugs it in the drag equation, and the drag equation also goes into this alpha drag term over here. So ignoring all of that math, the final equation for orbit decay rate, it's a simplified model again, boils down to this very simple expression. The rate of which your orbit decays is just simply the product of this drag deceleration, your Keplerian period, and this entire product divided by pi. So I shared a bit about this simple model in some paper that I wrote 2 years ago. And this actually really speeds up the orbit decay computation in orbit M as compared to using STK manually. So this is now a run-through of the Orbit M GUI. It's actually really, really simple T-Kinter kind of a layout here. If you git clone the repo, so no coding, you don't have to like pour through the code. You just need to run the orbitm.py, and you can specify what orbit simulator you want to use. You can use the simplified one, which I didn't know what else to call it, so I just call it SAMS. It can also, if you have an SDK license, you can also use it to automate your programs in SDK. This was not intended, but I did it anyway just to make sure that I can check it with my drag models results. So you input in your epochs, your spacecraft parameters, your orbit parameters, and you set your maintenance tolerance bands. As well as your margins. So for example, 200% margin means you have a 100% safety net. The output of Orbit M, it gives you a propulsion sizing chart. It shows you how your altitude will vary over time, as well as a delta V report. So this is a rough flow of the fast computation. The key idea is when I fall below a certain tolerance over here, I compute a first order delta V, apply it, and instead of doing a full orbit propagation as per commercial software, the only thing I do is just solve for this new change in the radius. And this takes into account, it's not just for circular orbits, it takes into account for elliptical orbits too. Whereas for STK, it does do a high precision orbit propagator, and it takes into account all of these four forces over here. So you have your sun and moon, you have a more comprehensive drag model, solar radiation pressure, the solid tides, and ocean tides. If you want to use, if you're an STK user, you don't actually need to switch on STK manually and create your own scenario. So simply by selecting the STK 10 or STK 11 mode, you can automate the entire STK scenario setup process too. The total runtime on like most standard workhorse laptops that I've tested on in my company, it takes about 15 minutes to run a 2 to 3 year mission in STK. Whereas in Orbit M, it literally just gives you the results in like 1 second. So it also outputs the first thing it outputs, you'll see that you'll have an additional file in your main directory, and it's called the Orbit Maintenance Scheduling Report. It tells you how many orbit maintenance, how many thrusts you would expect. And by default, the program is currently set to thrust at the apogee and perigee because we assume that the user wants to keep their eccentricity unchanged. So especially so if it's like a frozen repeat ground track orbit, right? And then it gives you a rough estimate of how often you need to perform your maneuvers. And finally, the delta V value. So because we use instead of doing some thrust optimization and complex computations, you just want to get a ballpark figure. So this delta V value is really computed just a first order Taylor expansion for the vis-visa equation. And so you see that every value is the same because it's the same first order that's used. It's the same amount of delta V that you need to cover your tolerance band whenever your satellite falls below a certain height. And now for the fun part. This is what the analysis actually gives you. So the blue lines, the blue plots are actually the fast solvers. So it's the very simplified, it's the one that uses the very simplified orbit decay rate, and you get the results out in like 1 second. The orange plots are the STK plots. So this is STK using high precision orbit propagator and astrogator. And so the left plot shows the mean altitude. The middle plot shows the mean semi-major axis. And the right plot is what would be useful to mission analysts or even to propulsion scientists like Michael Bretti's presentation yesterday in AIS, if he wants to size up certain propulsion units versus the class of mission types. So for example, microsatellite mission types would need typically at least 100 meters per second of delta V or more. And so you can see where your thruster lies. So nanoavionics, this is a thruster that's meant for cube satellite missions, whereas you see the Hall effect thrusters like the Busak, Eliana, and LAGP from Ukraine. These fall under the microsatellite ranges. They're meant for satellites about 200 kg and above. And as long as it exceeds the curve, it means that you have the height of this bar chart represents the mass of the fuel that this thruster can carry. So one thing interesting was that at least it shows as a ballpark figure, the fast solvers delta V or total fuel mass required on the y-axis is close enough to the value that STK gives out. So you can size your propulsion units easily on the right chart too, right? Because your mission lifetime is often dependent on how much fuel you can carry and what is the efficiency of your thruster, which is measured by this specific impulse here. So this mission was run for 450 kilometers. The parameters are given here. Then we did it for 500 kilometers mean altitude too. And not much difference in the trend of the results. At 550 kilometers, interestingly, and I'm not sure why, the propulsion sizing, the amount of delta V computed for the fast solver in blue matches the result from STK10 exactly on this chart. I think it was like an order of difference of about millimeters per second. So since most of the future LEO constellations will be around the 400 to 600 belt, at least this is at least it's a measure of confidence that it's not too far off from the, using STK as a ground truth, it's not too far off. So in summary, OrbitM is a Python-based orbit maintenance simulator. I thought it would be a useful tool for the open source community, which will help you to size your mission lifetime very quickly. It can also help you to determine what class of missions your propulsion units are suitable for. And it's most useful if your satellite design has many physical iterations with changing area to mass. So you can run like 20 to 30 lifetime simulations an hour, and you can get the results like almost instantly if you're using the fast solver. Yeah. And finally, OrbitM is looking for collaborators versed in GMAT, since STK, as we know, is on the orders of hundreds of thousands of dollars and it's not free. So if anybody here is well versed in GMAT and would like to contribute and automate GMAT orbit maintenance using OrbitM in Python, please let me know.
Excellent.
And with that, thank you. I forgot to put the most important thing, which is the repository URL. So I'll post it in the chat right
That's
now.
also a question here. Yes, thank you, Samuel. Thanks for the presentation. We'll start directly with some questions that we have already. The first question is from Leonard. What is the precision or accuracy between SAM and STK? I think you touched briefly onto that, but if you can summarize this a bit.
Yeah, so far we haven't tested it, okay, so I've tested it between 400 to 600 kilometers. I think the biggest margin was close about 15% difference. Usually SAM's propagator, or I wouldn't call it propagator, SAM's solver tends to overestimate your delta V. So that's kind of safe, right? Because you always want to overpromise, you always want to underpromise and then you overdeliver on your mission later on, right? So it's best to overestimate it anyway.
And what is the future of OrbitM?
I want to extend it to GMAT, because for non-STK users or users who don't have financial access to expensive satellite software, there isn't any alternative right now besides SAM's solver and STK. Right now I'm comparing it with STK. So I'm looking at either GMAT or as a land, also ORCID. ORCID could also be another. So you kind of you can run two simulations and then you can compare how close their results are to each other. And at least it's a sanity check that you're not too far.
I was wondering, since you did simulations and you compared, but did you also test it against real data? Because we have CubeSats decaying or deorbiting, I guess, once per week. There's so many up there, or other fragments or small satellites. And for some of them, I guess you can get some good tracking data to cross-check your algorithms.
Yeah, that's a good question, actually. So I've actually tested it also against one of our satellites, it's called Velox C1, and it was a microsatellite that's launched by Nanyang Technological University 5 years ago. So I managed to get the GPS data down, and when I tested out STK's, my solver, and the actual GPS data, it was a 500-kilometer orbit. From the back of my mind, I remember mine, because I was very proud that mine was closer. The actual decay was about 2.2 kilometers, and mine was like 2.3, and STK estimated 3.5 kilometers decay over, I think it was 1 year and 10 months. No, sorry, about 10 months. Yeah, it's about close to 10 months. Without any propulsion, it was close to that amount. I don't remember the exact figures, but the data for those decay values are given in citation number 3 when I was sharing it at SmallSat 2 years ago. Yeah, so
Good.
Actually, this project is an extension of that work so that everybody can access orbit maintenance easily. Thanks for the questions.
Thanks.
Thank you, Sam. And I think that would be all for this talk. And we need to move to the next one. Do we have Alex with us? And let's load the presentation too. Thank you, Arthur. And we do have Alex. Welcome, Alex. So, Alex and Chris, fantastic. We have both of them. I don't know whose intro should I do now. I guess I will start with Alex's. Okay, cool. Okay, for Alex then, he's a master's student in the electronic engineering with space systems at the University of Surrey. And today he's going to be introducing us on how can we improve the fault tolerance of commercial and off-the-shelf devices such as the Raspberry Pi and make them suitable for use in a space environment. So super interesting talk about dual redundant CubeSat flight computer based on Raspberry Pis. And with that, Alex, the floor is yours to indulge us.
Okay, brilliant. Thank you very much. So yeah, as you said, I'm Alex, and with me is Dr. Chris Bridges at the Surrey Space Centre. We want to talk about some of the work we've been doing about creating this onboard computer based on the Raspberry Pi platform. And this is something that's been under development for a while now, but today we want to launch it as open source and get your opinions on what's happened so far. So here's a quick overview of what we're planning to do. Firstly, we'll be talking about where this design's come from, why it exists, and then looking at some of the implementation itself. I'm hoping there'll definitely be some content in there that is of interest, even if any of you aren't necessarily interested in Raspberry Pis. And then we'll kind of look at a system overview, a function breakdown of some subsystems, and then wrap up by just looking at some characteristics in general. So firstly, I'd like to just ask Chris to give a quick background on the ARREST mission, which is where this has come from.
Yeah, certainly. So hello, everyone. Yeah, I'm Chris Bridges. I run the onboard data handling research group at Surrey Space Centre. Many of the student projects that we have going on at the Space Centre, we usually do these in relationship to missions. And one of the missions that we were working towards was called the ARREST mission, which is between Caltech, working in collaboration with NASA JPL, and IIST in India. And the purpose of this mission was to work and build autonomous reconfigurable space telescopes. And so what we were using is using a central core, which was roughly about a 6U, possibly even a 9U. Then we had some attached 3U units that we could then move around. So the systems that we designed are visual navigation systems, propulsion systems, but of course we need the computing to go behind this and the grunts to go behind this. And so Alex is one of many students who's been able to then sort of build and develop. And what we sort of do, and certainly in my research group, is we get opportunities to fly things and we get opportunities to do some really exciting tests. And Alex is the sort of culmination of that. So there's been a number of students behind that working towards this. But I'm so proud of him, and I hope you all can bask in what he's been able to achieve. And we're looking forward to some comments. Alex.
Okay, brilliant. Thank you, Chris. So I want to start off with a quick discussion of why Raspberry Pis might be a good idea for space missions. Obviously, I'm not here to try and sell the Raspberry Pi to you, so this is just my personal opinions on its suitability. It is kind of common sense stuff, really. So the advantage is that, really it's an inexpensive platform. It's quite simple to develop with because it's self-contained. And obviously there's a great community out there of, open source people and hobbyists as well. And that's really nice because if you have a problem with your own project, it's quite likely someone else has already done that and fixed it for you. Also, these things can be quite powerful. So as well as an ARM microprocessor, you've also got a GPU on board. And that can let you do all sorts of very efficient fun things with image processing and vector calculations. The disadvantages, again, kind of self-explanatory. Because it's COTS hardware, it's vulnerable to radiation effects. Now, we have done some radiation testing at Surrey. I know other places have as well. Raspberry Pis do hold up quite well under radiation, I think it's fair to say. But obviously, they're still vulnerable to things like single event effects and latch up. So it's something that's definitely worth thinking about still. It's also quite hard to physically integrate a conventional Raspberry Pi because of its form factor. But we've got ways around this. So our solution to doing this is firstly to try and combat that radiation issue by using redundant Raspberry Pis and then adding circuitry around them to support them on a single board. And then using the Raspberry Pi compute module, which is a lot easier to integrate than a normal Raspberry Pi. It's basically got an edge connector, and it's just a very small board, which you can quite easily fit 2 of onto a single PC104 size board, which is ideal. So you can get an idea of what this actually looks like here. This is kind of the evolution of this board. So as Chris said, it's a series of student projects over the last 6 to 7 years, different students every time. So it's gone in some slightly different directions over time. But it's evolved from what was initially quite a basic concept to something that's really quite tailored for arrest. And it's got some very niche features down here, such as an inter-satellite Wi-Fi link, which was necessary, and then also Raspberry Pi camera support as well. And then, of course, we've got the more standard things like I2C and UART support. Theoretically, of course, because that's quite a limited subset of all the buses out there, it is quite straightforward to add more buses onto that, depending on what the Raspberry Pi can support itself, and also changing the connect pin out to meet that PC104 definition that I see Pierre was talking about in the chat now. But yeah, the key thing to discuss here is really that in each of these iterations, there's always been some kind of onboard controlling device, and there's always been some kind of supply protection system. So in version 4, which is where we are now and what we're presenting, we're focusing on a digital supply monitoring system that really implements the entire redundancy scheme for us. So here's a quick system overview. On the left there, you've got the system architecture diagram, and on the right-hand side, there's some pictures of the board, but I've actually got the real thing here myself. So what you can see is we've obviously got these 2 compute modules on top, and on the bottom of the board, we've got all of the support hardware that you can see in that architecture diagram. What we're going to do is just go through some of these in detail in a moment, but I want to point out some key features here. Obviously, we're centered around these Raspberry Pis. They're connected to the PC104 bus via multiplexers. That allows us to switch between the Pis and implement the redundancy that we need. We've also got a microcontroller here, which is handling all of the switching for us. And as I said, again, that is really doing the monitoring and implementing the redundancy. We've got an Ethernet link between the 2 devices, which is quite important because it allows us to transfer data when running in a hot redundant mode. And then lastly, we've got our fun features, so our cameras down there and our Wi-Fi up here. So without further ado, I want to talk about the system monitoring system. And this consists of quite a few elements on the board. So we've got 3 regulator blocks, effectively, to power the Raspberry Pis and then also the Wi-Fi chipset. And each of these has a bank of current monitors built into them. These then talk to an analog to digital converter, which is then feeding us data back into our microcontroller that we can then use to keep an eye on what's going on with the system. I mean, the key idea really is just to monitor as much as we can, and if we see anything non-standard or suspicious, then we can take action to both keep operating securely and safely, and also protect our hardware if we need to. So as I said, all the regulator outputs have supply, current, and voltage monitoring. So if we saw something such as, a sudden high current, we might conclude that we've got a latch-up condition. What we can do then is shut that down as fast as possible to try and protect our hardware, switch over to our other system, which can act as our backup, and then hopefully allow us to continue operating with a minimal loss or delay. We've also got some status signals coming from our Raspberry Pi. The most interesting one being this heartbeat signal, which is effectively periodic and it acts like a watchdog. So if we stop seeing edges on that, then we can assume we've had something like a functional interrupt or our Raspberry Pis become unresponsive, and again, switch to our backup system. We've also got some monitoring systems on our Wi-Fi system, but I'm just going to gently brush over them because we're running out of time. So what we want to do is implement our redundancy scheme. So the microcontroller basically controls everything on the board. So regulators, Pis, multiplexers. It's responsible for just overseeing everything and selecting the active device. We're using an FRAM microcontroller here, and that's because FRAM does have some innate tolerance to radiation. And this specific part, MSP430, was actually chosen because it's got a rad-hardened variant that's also pin compatible. That is quite an attractive thing because this microcontroller is potentially a single point of failure. So being able to use something more robust there if we need to is something that's really great for us in terms of protecting our more complicated hardware. Moving on, I want to talk about the Ethernet crosslink connects, which is the other big part of implementing our redundancy scheme. Basically, we want to be operating what we call warm or hot redundancy. And this is where one of our Raspberry Pis here is the active device, and the other one is acting as a backup. And what we want is to be able to keep that synchronized so that it is up to date and can take over pretty much immediately with no loss of state or anything if the first device fails. And that requires us to have kind of fast data transfer between the two. just to let us do that synchronization in real time. So using Ethernet for this is quite a low-risk approach because it's already used on Raspberry Pis, but it's not actually implemented on the compute modules themselves. So we've had to do this ourselves. Now, the schematics for the Raspberry Pi Model B, which we see here in the top right, are actually in the public domain. So what we did is just basically take the circuitry for the USB Ethernet chip off there and implement it ourselves on our own board. Now, this does give us an Ethernet link here, you can see in the bottom, which is only a couple of centimeters long. We do have two transceivers, they're very close together. So it's kind of overkill from a hardware perspective. But it should just work in theory, and it does, which is great. We get an operational link that's giving us almost 95 megabits per second, which is great, because that lets us transfer data forwards and backwards as much as we need. I think I'm just going to quickly skip over the Wi-Fi, and we can come back to that if anyone has some questions, just in the interest of time. So the last thing I really want to go to in detail is this Raspberry Pi camera support. And this is quite interesting in how it achieves redundancy by supporting two cameras. And the reason for this is that traditionally the Raspberry Pi can't do this. So again, a lot of multiplexing is going on here. We've got lots of buses involved. So there's a camera serial interface bus, and then we've also got I2C and GPIO, and all of those need to be switched to be able to make this work. So there are some specialized multiplexing devices being used there. But depending on how this is set up, it can give flexibility and hardware redundancy. So what we're doing here is cross-strapping, and that means we can connect any Pi to any camera at any time. Again, that's great because it gives us that flexibility to deal with a failed camera or a failed Pi, whichever way around it is. We can even hot swap the cameras in use, which again is not something that Raspberry Pis officially support. But we found it works absolutely fine and it seems to be pretty much flawless. We functionally verified this, and this here is just a quick image to prove that you can actually take photos with this, and it does work. But obviously, there was quite a lot of engineering in the background to really get the signal integrity needed to make this work. So just moving on to some characteristics. Here's a picture of the board in testing. As you can see, it's operating on 5 volt and 3.3 volt supplies. And as I kind of alluded to earlier, the board is quite power hungry, mainly just because Raspberry Pis are very hungry devices. So we need about 10 watts peak with everything on the board running. For us, that happened to be fine, but I understand that for other people, that might be quite a lot of power to supply. There are things you can do, so you can just run one Pi at a time, effectively in cold redundancy, and that only needs 5 watts, but you're trading off the capability there, really. And for us, the next steps for getting this working are really focusing around the thermal profiling and RF testing, things that we need to be in a lab to be able to do properly. And that's just kind of an outcome of COVID, the fact we haven't been able to do this yet. And also because I was focused on the hardware mainly for this project, there's still quite a lot of software that needs to be developed for enabling the Raspberry Pi to work redundantly and to get that MSP430 working properly. So just onto the final slide as time sort of slips away from us. If you want to get involved, all the designs are freely available on our GitLab, which is here. That includes all the original design projects, schematics, Gerbers, reports, and documentation. And now for the slightly less good bits, if you want to look at it this way. This wasn't initially designed with open sourcing in mind. So I used Altium Designer to design this, which is kind of as far from open source as you can get when it comes to PCB design. Now, there are various converters out there for going to other file formats. And I am planning on doing a proper conversion to KiCad or a similar file format in the future. And it's also a fairly challenging board to assemble, mainly just because of all the complexity that's gone in and trying to squish the circuitry onto the board. I managed to put the whole thing together with a hot air gun and a soldering iron at home. So it is doable, but possibly not for the faint-hearted. It's a good challenge, either way. And lastly, it's a relatively affordable board to have fabricated and put together. We designed it for using the JLC PCB fabrication process, which means you can get boards fabricated for €7 a piece, which is great, although the components are a little bit more than that, obviously. And I see Pierre asking for Q&A, so there we go. Thank you very much. I'd love to hear your thoughts on this.
Excellent, and right on time. So thank you, Alex, for introducing us to your awesome project. And let's start with some, shamelessly, the first one is my question around joining for yesterday we had a discussion around PC 104, right, and the common definition, and it would be great if, since you're developing an open source, board, join the discussion.
Yeah, absolutely. I think that would be a great idea. It's probably something for Chris to deal with more, because I know he knows the PC104 pinout on that board better than I do. But you know, we can even change it if we want to be compatible with whatever the outcome of your discussions are. That's absolutely fine.
There was a discussion in about 2015, 2016 about how we can homogenize sort of all of these connectors back when SSE was first doing its first CubeSats. It might even be older than that, actually. And actually to get manufactured to fall to one thing is quite hard. And personally, there are probably better connectors than PC104 that can still maintain the number of pins and the mechanical stability that these things actually are used for. It's quite big for what it actually is.
Absolutely. And talking about connectors, there's a related question to that around the pipe board that are on the mezzanine connectors, right? And would that be an issue for space, like mechanically speaking?
Yeah, potentially. So obviously this is kind of a gold contact connector. It's kind of sprung in a way. It's not.
Do you want to go back a slide? Yeah,
oh,
and then
yeah,
you can see it.
There we go. Yeah, so here you can see we've got this edge connector all the way along here. And that's just effectively on kind of touching contacts on both sides. The answer is yes, in terms of vibration, that is an issue. But I mean, in an actual flight configuration, this pi would be securely bolted down at this end of the mounting holes. So it's fairly likely that in an actual operational flight scenario, i.e. not a launch, the vibrations may be benign enough that it is fine. If not, then obviously you can reinforce it with various epoxies and compounds, things like that.
What I would say is what we would usually do, and the things that we have to be careful of are things around conformal coating, and then there's a particular epoxy that we use in lots of our spacecraft called DP190, which is a horrible thing to use because it's really hard to get off. But once it's on there, it can really tie things down. So the edge connectors we would epoxy down, and we'd also need one of the things we need to investigate is whether or not we need the thermal strap to go across the processors. So whether or not these mounting holes here are kind of appropriate for that is something that we just haven't been able to do because unfortunately during Alex's project was impacted by the pandemic. But that's the sort of next thing we want to test in the new year, hopefully when all of our labs / vaccines start to become more available.
Another question around the compute module. We can see that you're using compute module 3. And what's your take on compute module 4 that is out now?
Hopefully we have some bonus slides here. Yeah, here we go. So I kind of anticipated this coming because it's been kind of all over the news recently. My take is that realistically, it's definitely a direction that could be kind of moved into. Although talking about connectors, it's using these very fine kind of mezzanine connectors, which are potentially even worse than the edge connectors we've already got. I think there's a little comparison about why we might want to do this here. But yeah, it can do things more functionally. It might simplify the actual carrier board itself. But again, the connector strength, it's actually harder to do the monitoring of the power systems on there as well. And also it's got no flight heritage. So as far as we're aware, there have actually been compute modules flown in space of the compute module 1, compute module 3 style. So that would be something that would be kind of disregarded if you did want to use this.
Yeah, of course. What we've been able to do is we've done thermal, vacuum, and radiation tests on particular versions, and of course, every time you make a change, it invalidates all your testing. So how kind of open source communities manage that level of risk, especially when they want to move up and do more exciting and more challenging things, is something for everyone to think about.
Excellent. And can you speak, I guess as a final question, a bit about the Wi-Fi inter-satellite link? Is it among the satellite itself or between satellites, the different satellites, if they fly information?
Actually, let me go all the way back to the arrest picture at the beginning. So the way this basically works is that you've got a core satellite, which is sort of the part you can see in the middle here, and it's got this boom. And you've got these two, what are called mirror sats. And the idea is these need to be able to undock, move around and do things like formation flying and redocking in different configurations. So the inter-satellite link is basically just to allow all of these to talk to each other. I'm quite happy to talk about the implementation of that later if anyone does want to know about that.
Yeah, I guess just very briefly, the main docking port interface uses electromagnetic docking systems to actually allow us to move things around. So we've actually done full simulations of the electromagnetic docking. So we can actually undock them first to begin with, and then we have to kind of turn on these very power-hungry electromagnets as well. So the Raspberry Pis are there because we actually have some pretty heavy GNC to do to then manage how we move these small satellites around. If they go probably beyond about 1 meter, then they're gone. And so the actual Wi-Fi system itself will probably go out to about 1.5 kilometers, because obviously it uses adaptive coding and modulation. So just like any Wi-Fi system, as the link gets worse, the data rate keeps dropping down. That's one of the things that we were going to be doing with our Indian partners. But the electromagnetic docking system and what the propulsion system was actually going to do is keep them very close. So things would be sort of happening in sort of space of 10-15 minutes, all within about a meter sort of cubed. So they won't be going very far at all.
Cool, excellent. So I think that wraps it up for this talk. And thank you, both of you, Alex and Chris, for introing us in this awesome project. And moving on, the next talk from Nico. Do we have Nico? And Arthur, let's load the talk. Nico, can you hear us?
Yep,
okay.
I'm here.
Excellent, and we can see you too. So thanks for joining, Nico. Arthur, do we have the slides loaded?
You're muted, Arthur.
So while Arthur is setting up the presentation, I'm going to be introducing Nico for the rest of the crowd. So Nico Carver is a librarian at the Harvard-Smithsonian Center for Astrophysics in US. He has been one of the people in the team working for a new initiative called the Library Space Technology Network. And that this is the project that he will be introducing in his talk. So basically, when you imagine of a library, what do you think of, right? Like a place full of books and people quietly reading their books away. And while this is a stereotype that is quite common, the truth is that this is only a small part of a modern public library. And today, people of all ages go to their community's library to engage with technologies that they don't have access to at home, including the internet, printers, scanners, 3D printers lately. And we soon hope satellite ground stations. And that's what Nico is here to talk about.
So there's a bit of a problem. The PDF is too large for upload.
Oh.
Wow.
I was supposed to prepare the session. Red One told me he's doing it, so that's why this presentation now is missing, and that's not working. There's another way to do it, which is
share the screen.
Yeah, share your screen. Can you do that? Or
Nico, is that okay?
Nico, I make you a presenter.
Okay, hold on 1 second.
And actually, the record of the biggest PDF goes to you now. We had what was it? 7 megabyte one yesterday for lightning talk, and now 33. Okay, it works.
Okay. So yeah, thank you, Piero. Sorry for the technical problems here. Hopefully this still works. And thank you for that introduction. It's great to be here at the open source CubeSat workshop. I'm going to be giving an introduction and some updates on a project we've been working on in collaboration with LibreSpace Foundation called the Library Space Technology Network, or LISTEN for short. And the reason that we want to bring ground stations to public libraries is that we think that this is an excellent way to broaden access to open space technology. And public libraries are a good place for this work to happen because they attract a wide variety of people from all different age groups and socioeconomic backgrounds. And the basic idea, at least for this pilot stage, is that we want each public library in the LISTEN network to build their own SatNOGS-powered satellite ground station, install it on their library's roof, and get it running and operating with the involvement of their library community, meaning the people that actually come and use the library. And we're still in the pilot stage of this project. And so what we're trying to do in the pilot stage is understand all of the potential pitfalls and limitations, but also opportunities to look for when we expand the network. And one thing that we were really cognizant of when we designed the pilot is that we wanted to pick libraries that we thought represented all kinds of different libraries around the globe, because it would have been very easy just to design the pilot to choose libraries that are really well funded and well staffed that could do this kind of work quite easily and successfully. But what we were trying to do was be aware that there are all kinds of different libraries, and so we didn't want to pick one that just couldn't do the project, that maybe just didn't have the available resources to actually successfully complete it, because we know that would be frustrating. But we also just didn't want to give the ground stations to libraries we know that this would be really easy to, because they already have a huge technical staff and people willing to do this kind of thing. So in an attempt to prevent situations where we didn't think that the network could expand to all the different kinds of libraries out across the globe, we came up with a bunch of different criteria for picking the libraries. I won't read them all off here, but we wanted to represent as many different social, cultural, financial, technical, and geographic considerations as we could. And so the geographic part, we knew going into this pilot that we wanted one library in the Eastern Hemisphere and one library in the Southern Hemisphere, because we felt that those areas are often not represented well in projects like these. And so that was one criteria, but then we came up with some others to help guide us in picking libraries, because in this pilot, we decided who to reach out to install the ground stations. And so with that said, I'll just go through quickly here the 5 libraries that are part of the pilot. The first one is my home library, and so while we are connected to both Harvard and the Smithsonian, we are also a public library, in that we're open to the public and help members of the public. And we picked this library mostly because we wanted a place where we could test out what we were doing firsthand, and it was the first ground station that we installed on the roof of the Center for Astrophysics. The second library we identified was also local to us in Cambridge, Massachusetts, and the reason we picked another local library is that we wanted to have a place where we could do in-person activities and try them out before bringing them to other pilot participants. And so that idea got a little bit sidelined because of the COVID pandemic, but we are still working with Cambridge Public Library, and we think that that'll be a good connection to have like a local place to work with youth groups and things in the future. And then the first library sort of outside our home base is the library in Chisinau, Moldova, and this is representing our Eastern Hemisphere, and they've been really great to work with. You can see here on the right, they brought together some kids to start building their ground station and hope to install it soon. And then our Southern Hemisphere library is the Biblioteca de Santiago in Santiago, Chile. And they've been mostly shut down since COVID, but we were able to get them at least the listen ground station and confirm that they received it. So that's sort of where we are with them, but we hope by the end of the pilot still to install the ground station there. And then one other kind of library we wanted to represent in the pilot is a rural location, meaning a location with not many people around, not near a city. And so the location we found for that is a little town in West Texas called Marathon. And it's just a few hundred people, and they have a very small library and just one librarian. But she's been great and willing to work with us to try out this pilot. And so they were the second library to completely install their ground station and get it working. And we've had some difficulties with networking that continue. They've replaced their router, and we're hoping to get it back online soon. I'm not sure if that's due to the rural location aspect of it or not, but all of this kinds of information about, what could go wrong with the Listen project is what the kind of information we're looking to get in this pilot, because we want to know of all potential pitfalls before we could expand the network. I'll move on. And so after we picked our pilot locations, the next step in making this project work was developing a Listen kit. And Freddie mentioned this at the SatNog State of the Union yesterday, because it's thanks to LibreSpace and SatNogs that we were able to put together this really easy to build UHF station. And so LibreSpace tested out a prototype build in Greece, and then we bought the same parts and tried building it ourselves. We modified just a couple parts, and now this is the Listen kit of 11 parts. It's easy to put together, no soldering. You can just put it together with a screwdriver and install it, and you have a really capable UHF station. And so one thing we knew going into this project was that we wanted to make this really easy to follow for people that have no technical background. So this is an example from our website where we try to explain what every component of the ground station does. And then we also have come up with very detailed documentation. We think that a lot of people who come to open source CubeSats and ground stations probably already have some of this technical background, but we knew that the library communities might not have the technical background, but might be interested to learn. And so we wanted to come up with documentation that was very detailed and easy to follow for novices. And so the main source of this documentation we're compiling into a Creative Commons licensed work called the Listen Handbook. It's available for free online, but for pilot participants, we also printed it out and made it a physical handbook that they can have while they're working on things. And the first step in that handbook was to make very detailed build instructions. And so in developing these build instructions, we include lots and lots of pictures. One of the reasons for that, other than it just makes it easier for anyone, is that we are targeting non-English speakers too. So we have the location in Moldova and one in Chile. And so the native languages in those places are Romanian and Spanish. And so we wanted to have the pictures so that maybe they could follow those without even understanding the English fully, but we're also working to translate the English into Spanish and Romanian to make this even more accessible. And beyond the handbook, we're also developing other educational activities. Our first idea for the pilot was that we wanted to do in-person activities, and the first one we wanted to develop was an in-person build activity. So the idea was that you would have all of the parts that we send to you, and then the library community would come together to build the ground station. And it looks like Moldova actually was able to do that during COVID, but most of our other libraries, because of the libraries being shut down or social distancing rules, have not been able to do an in-person build activity. So we have shifted our goals a little bit with the educational side of this and have been focusing on online activities. And one of the first ones we developed was this satellite communication activity. And the idea here was it would introduce people who come to this to satellite communication. There's a hands-on component to it too. There's a video, but then there's a hands-on component where we've slowed down the audio from VZLUSat-1, which is a Czech satellite, and so that participants can actually hear the Morse code in the continuous wave and learn sort of what that sounds like and learn how to decode Morse code by hand. And we have ideas for other online activities, and we've started developing some of those, including a very intro presentation to the whole project. But we're also soliciting new ideas, and so these are ideas that should be fun for novices that could just complete these activities with just the Listen kit, which is again a UHF station. And so if you have any kinds of ideas for Listen activities, I can put the link in the chat in a moment, and it's just at lstn.wolba.ch/resources. There's a link to this activity form, submission form. And it just has very basic information, but we found that there are people outside of our working group that have really good ideas for educational activities. And as we expand this beyond the pilot, we're really hoping to develop a curriculum around working with a ground station, but also understanding about small satellite missions and open space technology. And so to wrap up with Listen, what we're hoping to do is to get public libraries around the world involved with real space technology by lowering the cost, but also the technical hurdles of owning and operating a satellite ground station. And with that, I'll open it up to questions. Thank you.
Excellent, right on time. Thank you, Nico. Maybe Arthur, can we get or you could keep Nico up your slides.
Okay, sure.
For that, while we go to some questions that we have.
This one was already. I think you already answered that one about Juan Luis is asking to get in touch with if you can get in touch with the Chile library. He's asking for a friend. Maybe it's that one or.
Sure. Yeah, I could do that. Let me see. Yeah, if he wants to just reach out to me through a private chat, I can hook him up.
Excellent. And there is a related question around which you already kind of answered regarding the other languages and if you're open to translations for the handbook.
Yeah, I think we're looking at the funding. Spanish is definitely our highest priority because it's a language that's spoken in a lot of countries. But we're definitely open to translations. Yeah.
Okay. Then another question would be, what have been your biggest challenges so far?
So I think on the technical side, we haven't had any issues with building the ground stations, which we didn't really expect would be a big issue. But the biggest one has been networking, because it's hard to plan without knowing, because all the different libraries in our network have different networking setups. And so it's hard to write really detailed instructions about how to set up the Raspberry Pi on anyone's individual internet network.
And another question would be about the next steps after the pilot.
Yeah, so we're hoping to both expand the network beyond 5 libraries, of course, but also to develop a curriculum. So right now, these educational activities that I've been describing have been sort of just like one-offs, but we're hoping to actually develop something that would follow pedagogy and be like, you could start with the basics of learning about satellites and then build on your knowledge to learn more and more about it, to eventually get to the point where you could get involved with open source projects.
And while you are on getting involved, what would be the best way for someone to get involved in your project?
you can go to the website, which is lstn.wolba.ch, and there's contacts there, but also that activity form that I mentioned. Yeah, and so that's probably the best way is just to contact me, and I can put you in touch with everyone else.
Excellent. Thank you, Nico. I don't think that we have any other questions, at least on the channels that I see here. Oh yeah, there's another question from Samuel. Did you face any legal hurdles in the project about the ground station listening to the broadcasts, and what's the legal aspect to it?
Yeah, so that was something that we initially we had been working with some governments or not, I shouldn't say governments, it's skipping ahead. We started working with some libraries in Africa and found that they often needed approvals from their federal ministries of culture to go forward with this kind of project. And it presented a thing where there seemed to be so much red tape that it would eat up all of our pilot time before we could start working with them. So that was one of the legal challenges. We also have had questions about, can we do this legally in our country? And sometimes the answers to those questions have been unclear because we don't know enough, we don't speak the language. And so we have had some legal issues, mostly just not knowing. And so one of the things in the next stage of Listen is we want to hire a legal consultant.
Okay, cool. And I think that would be all in terms of questions. Thanks again, Nico and team, for the project and the presentation. And with that, that concludes our first session of the day, and we can move into break. Arthur, any logistical points?
No, nothing logistical. We have now, almost 20 minutes break, which is very good. Get a coffee or something, and then we head over to the demos and tutorials sessions.
Lightning talks first, yeah.
Lightning talks first, yeah.
Sorry,
Here,
lightning talks, yeah, right.
Yep.
Yeah, actually, so we finished early, so that's the opportunity for me to tell you, but presenting my son, to tell you that if you have ideas that you wish to have in the lightning talks, please reach out to me. I think we have 1 or 2 slots we got free.
Cool. See you all in a bit. And in the meantime, can we get some whiteboarding activity happening here?
Yeah.
Thank you. Oh, it's going to be on the arrest mission.
Go.
Someone playing the piano.
All right, 1 minute to go. Anyone with a blockchain idea? The digital drawers, you're amazing.
Hey, Bo, you certainly have to speak with Piers on that.
Yeah, you should use 4 minutes to tell us more about cubesat, even if it's not you.
I don't think so. It's well, actually, we don't know at which point it's serious or not. So
I haven't checked, but
me and Artur have been on
Space Chain, yeah.
not.
Yes.
You remember what we've seen in the Ohans? Hunting satellites visually with telescope cameras. Oh, Artur is having a beer. Are you having a beer?
Yeah, me too. It's just.
Whoa, nice!
And I'm just having coffee.
It is a coffee, latte macchiato.
Okay then.
All right, everyone. So, welcome to the lightning talks. This is the moment. So you have 4 minutes. Each of you subscribed. Of course, you can jump in. We have, I think, 1 or 2 slots that are free. I'm not sure I see the 2 last. Oh, Diego, you're here. That's perfect. And you have 4 minutes. Slides, no slides, you choose. Sharing your screen was discouraged, but if you didn't share your slide, you should have to share your screen now. And for you, Damien, I have your slides, so we'll start that up. So Damien is French. Bonjour Damien, comment ça va? Good. It's part of Federation, so I think inspired name by Star Trek, and they are doing open source space in a way, right? So you're going to talk about the Phoenix project, and give you the screen. Take it away. You have 4 minutes. Go ahead.
Just trying.
Oh, right. Let me just give you the permission rights. Damien, I just have find you in the list. Oh, here. Perfect. Oh, thank you, Arthur.
Just testing. Okay, it works. Okay, let's go. So hello everyone. So I'm a member of the Federation Initiative. I'm going to talk about the Phoenix project, which is launched in the frame of the Federation Initiative. Just to explain what Federation is, Federation was launched by the CNES, the French space agency. It's carried by an association of volunteers, and the mission is to enable individuals to design and manufacture open source hardware with no requirement, skills, experience, diploma, or network, only in energy and passion. So how are we doing that? Well, it's right here. So we're doing that through 4 main pillars. We have a Federation Charter, which is our legal base. We have a collaborative web platform, so it enables project management, collaboration, publishing the results of the projects. We have a network of enthusiasts and Fab Labs, so local manufacturing associative place around space projects, and we bring support by material and financial means to projects. Open source is at the heart of the Federation Initiative, first to ensure sustainability. Everything that is produced within the Federation framework, both failures and successes, can be improved by anyone and serve as a basis for the creation of new projects. It's also a protection. It serves to protect the work of each individual who are involved in the projects. Some example of the projects we are leading. So what you can see here is a electrical rocket stage electrical separation system. So an initial prototype flew on a mini rocket in 2019. So that's what you see on the right hand side. And the second version is being finalized and will be tested in flight in 2021. Another example of projects a bit more ambitious, you may know some bricks of the THEMIS reusable rocket stage demonstrator, which is developed by Ironworks, are opened within the Federation initiative and under a THEMIS Open umbrella project. And so volunteer members are now working alongside Ironworks employees on concepts for 2 of these bricks, which could fly to the edge of space in 2022. Still further, we have Mars-proof. Mars-proof is Israel for Mars, so producing locally all elements to sustain an autonomous human base on Mars. So the team is working on designing and making demonstrators on Earth with the aim of sending refined version to Mars in the 2030-2040 timeframe. Now about Phoenix. So Phoenix is an open source orbital cloud infrastructure. The objective is to design, build, and put into orbit the first bricks of an orbital cloud. So what's a cloud? If you're not, it's a shared IT infrastructure in orbit, basically. So this cloud, it provides shared compute and storage capacity accessible from anywhere across the internet. And this cloud will be based on decentralized and a modular architecture. The objective is really to make, we are not going to put the full constellation overhead. We're going to enable any organization on a global scale to contribute to the deployment by incrementally adding standardized and open source bricks to the infrastructure, be they space or ground segments. So the aim is to provide space-to-space and space-to-ground IT container services, which could be put to multiple uses. Once you provide a Docker, you can do image computation, trajectory computation, signal processing. The main components, not what is written in the slide, was a generic slide, but main components is the IT architecture itself. So each satellite will constitute a node of the infrastructure. So mainly information processing and storage, that's a server, or a communication node, that's a switch. Then we'll have, of course, the space platform itself, the communication system, intra-satellite, 30 seconds, okay? Intra-satellite communication and communication with the ground, and of course, the ground segment. Our current roadmap, testing the early software layer from an existing orbital platform, ISS or satellite, in 2021, that's next year, launching a 2U proof of concept in 2023, and launching the first nodes of the operation constellation in 2026. We are currently in the design phase. So the project was launched 2 months ago, very early. We are using the model-based system engineering methodology and using what you see here is open source Capella software. So it allows us to go from the system interaction with customers and ecosystems down to the logical and physical design. From the previous slide, operational analysis level, we deep dive into the system architecture at the system analysis level here, and from there we will go down into the logical design within the next few weeks. So you are welcome to contribute in the next steps. Join Federation. One twist is that the platform was initially launched in French, but until recently it was only possible to join in French. We have just recently added support for 4 additional languages, including English. Be merciful with the work in progress with other languages than French.
No worries, no worries.
Welcome to contribute to the translation efforts. So we're looking forward to accelerate the pace of innovation.
Thank you, Damien. Thank you, Damien. So for Damien, please, you know the rule like yesterday. So give a yes or a yes, a big yes or a small yes. What's your yes now? I want to hear it. Yes. Very good. Okay, next on stage is Baris. So Baris, I will prepare your presentation. In the meantime, in parallel, I present you. I am multitasking. This is amazing. So Baris, you see his camera behind him. You have some kind of a fab lab. You know, it's like you must be the local fab lab. Who did?
No, this is my living room.
Yeah, but that's.
I live here.
I don't know, Arthur. You have to prepare.
Sorry,
no worries.
And let's see. Informant is how fast we can talk and how much we can tell about the project.
Yeah. Anyway, this looks super interesting. A transportable SDR transceiver. So, Baris, where are you standing right now?
I'm in Helsinki now, but originally I'm from Turkey.
All good. Then the screen is yours. You can go. 4 minutes.
Yeah, I will talk about an SDR transceiver, which I was dreaming about. There are many HF SDR transceivers in the market, but no VHF, UHF, or upper frequencies. I was looking one for working with meteor scatter, moon bounce, or satellites, but there are many strict rules for those. That has to be durable, reliable, etc. So I give up with that up to when I come searching for what's in the market as open source. First, I figure out that there's PSDR. I think it's not going on anymore, but it was a very good project. Then I worked with Monka. Monka was the perfect one with the source code. I read all the source code. It's perfect, except the hardware is not as simple as I was looking for. It has very good designs for external mechanical designs. Everybody copied that. It's a very good project. And while I checked all the SDR implementations, there are a lot of good UI interfaces that I can use. That's amazing for me to start somewhere. Then I come up with Barbaros WB2CBA introduced me the USDX, which is as simple as I can find in the market. It's only a few hundred lines of Arduino code and a very, very simple hardware you can build, let's say, in $30 or $40. So I decided to use this as the base of my design. Then I need a project, not a moon bouncing solution, but a QO100 satellite communication ground station might be good. Let's make it interesting. I decided to make it portable. So I started writing the requirements first. It will be software defined, it will be portable, it will be cheap, it will be very simple that everyone can experience. It should be expandable so everyone can put their ideas on it. It should be battery powered because it's portable, it will be stable, and the first rule, it will be open source, collaborative, and non-profit. So what a commercial setup looks like, some up converters, some down converters, and then SSB radio at the end, which is the most expensive part. So I decided to replace that radio with two USDX receivers. Why two? The rest is my prototype. Why two? Because I would like to have a frequency stability. I checked the STR console software, you might know. It's using a very good function following the beacons to stabilize the frequency. So I decided to use the same. We're having a second receiver on board, so the frequency stability will not be an issue. This is an overview that you can find in the GitHub page as well. So what will it look like? It will look like, it will fit a backpack, so you can carry it anywhere. It will have at least as less as possible moving parts, so you can easily set it up and start working satellite. 10 gigahertz downlink and 2.4 gigahertz uplink with at least 10 watts of power that can work in any mode, including SSP and FT8 kind. So the stage of the project is in the early prototyping phase. I have a bench testing setup, so I have some QSOs with this setup. I roughly have 4 to 5 watts output with this setup, and it's working great. And what I'm looking for, or what we are looking for contributors, because what I believe is the spirit of open source is having contribution to your project. So we are looking at developers, PCB designers, makers, mechanical designers. Anyone is welcome to our project. We have tasks for everybody to collaborate. And that's it. Thank you very much. These are the GitHub project pages.
Perfectly on time, Baris. Awesome. This is amazing. Great project. So I wish I had one right now. This is cool. So I think everybody is seeing awesome projects. So please reach out to Baris. He's here. You'll be there after, I assume, and you'll be there at the launch time. So
thank you for giving me this opportunity. Thank you.
This is great. Thanks a lot, Baris. So for Baris, please give your yes.
Yeah.
Yes. Great. So next to come up is Jan Peter. Jan Peter, I give you presenter right now. So Jan-Peter is in the Polaris team developing the Polaris project, but is also keen on podcasts. The irony is that your audio doesn't work very well, and because you're still waiting for that gift for Christmas. That's it. and so he has
welcome
a
everyone to my
presentation.
lightning talk.
Yeah, okay.
Very
good.
Welcome
So
everyone
you
to my
have
lightning
4
talk.
minutes. I see your presentation is 3 minutes, so that's just perfect. So the screen is yours, and please listen to what Jan-Peter has to tell you. Maybe you can do lip sync. Go ahead.
Where I want to persuade you why it's a good idea to launch a podcast about space-related open source projects and why you too should participate. But just before I start, you may be asking yourself, who is this person and can I trust him with my project? Well, hello, my name is Jan-Peter, I'm 28 years old, and I study and work at the Technical University of Darmstadt in the field of space systems and machine learning. And can you trust me? Well, they did. Right now, we know that there are existing open source projects, but especially if you're new to the field, finding these projects is not that simple. Or maybe you heard about a project but want to know more about it. Or maybe you want to know about the latest updates. And if you're part of the project, maybe you are missing just that one specialist. And all of these things take time if you want to do them yourself. But luckily, the internet people have invented one medium that can be applied to almost any situation. I want to launch an audio interview podcast where I talk about space-related open source projects with the actual people involved. And to make it easy for everyone to follow the idea of the project and to put it into context, I will create a map of space technology where every project will be located in. The podcast will have 2 types of episode. An introductive interview where we talk about the topics like the general idea of the project, its history, present and future. And an update episode where every time something major happens, like a bigger software update for example, we meet again to discuss the news, changes and things like this. Each episode will follow a similar agenda, where we start beginner friendly with a high-level introduction and then dive deeper into the details of the topic. The podcast is first of all targeted for all of us, the OSCW community, but of course everyone is welcome to the party, like general space fans and the actual users of the project. Now here comes the moment where I need your help. Behind this QR code you will find a survey with 7 questions, and I would like you to answer. With answers to questions like the preferred duration of the podcast or beloved topics, you can help me make the best podcast for all of us. You can see the link to the website and the QR code to the survey over here, and for those of you that are interested in the technical details, the tools that we use to produce the show and the timeline I have planned for now, you can have a look at the extra slides on my website. Thank you for your attention, and hit me up on these channels to learn more and discuss ideas.
Oh, lovely! You did amazing. I mean, that was just great. Every presentation could go like that. We should make like, yeah. You're the space reindeer. Whatever. All right, somebody like transmitted your link. So they could fill up your survey. Thanks a lot, Jan-Peter. So podcast for open source space, how good is that? Give me your yes or your yes. I want to hear it.
Yay!
This is a big yes, Jan-Peter. You have to go forward. This is good. Thanks a lot. So next in line, we have Mantos. Mantos has no slides. This is amazing. So let me just put a random slide. So Mantos is part of the LibreSpace Foundation. Is in every project as I recall somehow. There you go. So
presenter.
Yeah. You want me to make you presenter, right? You know how to do things, right? I don't know what's happening with the presentation right now. Make you presenter. You decide. That's it. Room 1. You can activate like drawing, but that's up to you. You have 4 minutes, and this goes from 5-4. The screen is yours. Oh, you're sure?
Okay. Yeah, I'm sharing my screen. So
All right.
it's working. My system is on green mix, but I'll try to make it. So while open source in software world is well established and actually devour everything else, and while in electronics is also becoming a standard with KiCad nowadays and with some other software, in mechanical is a bit back, and there were some very like primitive solutions and for 2D design like KiCad that then renamed in QLibreCAD, no QCAD LibreCAD, and also the thing that the software guys believe about hardware design, which is OpenSCAD. So luckily nowadays we have FreeCAD, and FreeCAD nowadays is getting better and better. And after the awesome failure of the how it's called F360 or something, now it has a lot more people, and the community is becoming better and better. This is the design of Cubic in FreeCAD, and this was something that was really, really helpful. And it was this is a fuse between KiCad and FreeCAD, and you can see how deep the design is. And this design is made by Agis actually, and here you can see like that this tiny inductor is fits exactly between the connector and this like screw. So this is absolutely mandatory in order to design something that is so small and everything is super, super tight. So after the design, something that's becoming more and more useful is finite element analysis, and there are a lot of open source tools for finite element analysis, but they are like just text-based stuff that you need to put some nodes and do the calculations. So FreeCAD also nowadays becoming more user-friendly in this area. This is the finite element analysis of the Picobus deployer, which is a pocket cube deployer, and this is a quasi-static test, I think. And here you can see how it is performing on, I think, 4G quasi-static load. And also there is Elmer Solver. This is something displayed in ParaView. It's a program to display those kind of analysis data. And this is a model of the Saturn.coms, a project we are developing. And this is a thermal simulation with radiation also. So those external panels are radiated by sun and radiate back to the board. And the last thing is what they said in mechanical design was CAM, is called CAM, and it's computer-aided manufacturing. And here you can see a component done by Elias, and this is a component that from Picobus, and those are the lines from the machine can take to carve this out from a single piece of TFE. So I think I'm on time, and I'm waiting for it to kick in. Come on.
Job, awesome. Thanks, Mantos, the mechanical guy. So design for space. That's good. So thank you, Mantos. Perfect on time. Thanks a lot. You were breaking a little, but we could hear you. And you have some questions. I think you can start discussion with them. But I want to hear the yes for Mantos about those. I want to hear.
Yeah.
Yes. Oh, big yes, Mantos. Maybe because you look like Lenny Kravitz. All right, so Diego, you're next. Diego, you're next. I will give you presenter rights. So Diego, I'll make you presenter. You know the rules. You have 4 minutes, and the screen is yours. Feel free to talk about your picosat approach. This is nice. All right.
Sure, upload. Is the external video?
No, it's next to the camera, maybe. Have a look next to the camera.
Share your screen. Sorry. Yeah. Okay.
No problem. So, Pico fluid dynamic actuators in CubeSats. So that's you.
Great. All right, everyone. My name is Diego Garcia Cacho. I'm presenting on behalf of a Fluid Access team. They're in the chat here. There's some of them seeing in YouTube, but I'm happy to be here to talk to you about Pico fluid dynamic actuators in CubeSats. Let's get into it. So what are these PFDAs? Normally, of course, or the most well-known actuators inside CubeSats that are able to provide attitude corrections are reaction wheels. And basically, these are flywheels that are going to be sped up by electric motors and thus providing this, generating this angular momentum. What PFDA does are imagine these hollow cylinders that are inside filled with liquid metal, and we have an electromagnetic pump that's going to be turning on and off and providing this fluid with acceleration. That's going to drive the fluid inside this channel to generate angular momentum. So what's the kind of like, these are the two basic operating principles. We don't have many moving parts inside PFDAs, so this allows us to not worry about ball bearings or wear on the channel. We don't need any lubrication, or these are some of the things that commonly plague different reaction wheels. What is also really nice about PFDAs are they are very low friction, so we can provide constant torque at really small angular rates. And if you ever had pointing issues where you've seen a little bit of jitter due to the unbalanced nature of reaction wheels, this is something that the PFDAs are very good to handle. So this is what makes them really an interesting choice of actuator. So let's talk a little bit about them in another sense, like in a whole integrant sense. Imagine that PFDAs are actually really agile actuators. So they allow to be sped up really quickly and decelerate really quickly. So we can add to the list of capabilities that our small sat will be able to use. And we'll talk about it a little bit in the next slide. But I also want to let you know that, for example, these reaction wheels usually are very bulky and take up a lot of prime real estate inside our very small compact CubeSat platforms. And what with PFDAs what we can do is we can actually optimize for volume, and we can allow a lot more of that volume to go into payload. We can have multiple cameras, we can have bigger lenses. If you take kind of like this picture of what the 3-axis configuration of what PFDAs look like inside the 1U CubeSat. Right, so what's really nice about PFDAs in terms of what they can enable our CubeSat platforms is that with their agility and with their ability to be able to be sped up quickly, we can do artificial swath increase and single space stereo imaging, which are really interesting pointing maneuvers that we talk even about in the reference, and we'll be here also in the chat. So if you want to learn a little bit more about those, we're happy to let you a little bit in on that. So this is our first kind of like as a group, our first dip into the open space community. We've been very helped by different open source platforms. So we want to like bridge these fields, these gaps, and we want to kind of find ways of collaborating with different people in this open source community. So I'll end it right there, and I'll be in the chat. And thank you for your very lightning attention. Thank you.
Ah, very nice, Diego. Very cool. So, do you plan to open source the hardware?
Let me go over here. Okay. So, of course, it's not just me in this initiative, but we're all the people that's contributing to this project that are part of Fluid Access are definitely very willing to start opening up what we think are gaps in the ADCS subsystem that is a real step up for CubeSat builders.
Very cool. we'll be looking for you then. This is nice. You have like interesting questions in the chat. Does it make bubbles and everything? But for now, I just want to hear a yes for your project. This sounds so cool.
Yes.
Yes. Thank you, guys.
Yeah. So please stand by, stay at the launch time, and have those discussions with everyone. That's the goal, really. So we also kind of can make some breakout rooms for that. Thanks a lot. Thanks a lot, Diego. So now we're going to start the tutorial phases. Thanks for this. All right. So we have 2 rooms. So first room will be I'm here. Will be managed by me, and room 2 by LF and Eleftherios. So the first one is on demo on writing, loading, installing, and executing your code on OPSAT. So we have people from ESOC around for doing that. And we have on room 2, we have RESTful data storage and visualization. So this would start in 5 minutes. You can take the time for a bio break or to get to know each other right now. I will actually, since we have 5 minutes, I will do a breakout room. And this means that you will be split in different groups. I make 10 of them, so this will be like 4 people per room. So please say hi, get to know each other. All right, number of rooms. Oh, 8 max. All right, duration 2 minutes. You have 2 minutes to say hi. Randomly assign. Let's go. Did it work? It's working. I hope I'm not breaking. Big blue button. So we have people in different rooms. This is great. Good. And here we have Electra. Hello, Electra. We have Arc Martin. Arc Martin. Freddy, George, Elias.
Red, did you not select us? That was randomly everyone else, right?
I don't know actually. This I think yeah. You can move room. You can join another room if you want. Okay, Elias is alone. Manfred. I'll go see Manfred.
I'm not sure if this worked. I can see some different rooms. Red, you're muted. Well, actually, you're on room 6, so yeah.
The room that we just went in went away.
Okay, at least we found something on Big Blue Button that did not work as planned.
I'm not unmuted. Okay, good. Everybody's back, I think, now. This is good. Okay. Bo, you're not on the audio. Maybe you're going to room 2, so it's time to jump to the other room if you want to go there. So if you stay here, you'll be experimenting how to write your code on OPSAT. And if you go to room 2, you'll be doing RESTful data storage and visualization with Artur. All right. Yeah, I thought that was more synchronously done, Fabian. Yeah. All right. So, George, are you here? George. George, press and make you presenter. You have the earphones. I think you have the sound, so you can hear me. Very cool. We can't hear you. You have to actually log into the sound system. So click again on the sound and click again. Mm-hmm. He's doing the echo test. Guys, you're so creative. That's amazing. Dave should go first. Okay, where is Dave? Dave. Hey, David, that's good. So you're just muted, so you can unmute yourself. We can hear you.
Can you hear me?
Yes, perfect.
Yeah. How do you, Red? Nice to
Howdy.
see you again.
Been a while. It's been a while.
It has.
Yeah.
The slides, are they already there, or how does this work with the slides?
Let me check for you. Do you know your presentation name? I don't think we have anything from you here.
Oh dear.
Yeah. But you can. I don't have any material.
It's all from. Oh dear me. Oh, we have a mess here. I now I realize I didn't send it to you. Oh.
It's okay. I thought you were sharing your screen and going through the ISA VPN.
I could. Yeah. Okay, but there was a. I can share my screen, but is it?
You can share your screen. Yeah.
Okay. How do I do that?
So let me give you presenter role. Let me get out of the thing. I give you presenter role, and you should see a new icon next to the camera icon on the bottom in the middle. It should be on the right side.
Okay, good. I'm going to share my screen.
Great. It's loading. Perfect.
Okay. Oh, that's good.
Super. Oh, the good old PowerPoint style ISA.
Oh, yeah, you remember that.
I missed it. Yeah. All right.
Oh, you are so funny. Okay, guys. So can I just start?
Yeah, go ahead. Go ahead.
And then I'll lead into my team. Yeah, because I want to keep this very short because I mean I'm just the project manager of OPSAT. The guys who are doing the real work and the real creative stuff are gonna show you the stuff afterwards. But they just asked me first to just go over the concepts a little bit. So that's OPSAT there. We launched it in the 18th of December last year. So we're just coming up to our, in 5 days, it'll be our 1 year in orbit. It's the first nanosat to be directly owned by ESA and controlled by ESOC. So it's, you know, it's not a normal CubeSat. And it's a lot of work being put into this. So it started in 2012. And there's a lot of money and investments in it. And it's basically 2 satellites. So it's a satellite within a satellite. I don't know if you can see my mouse, but This is at the bottom. This is the actual CubeSat itself. And then everything on top of this is the peripherals, which are actually the experimental stuff. So this is I would say it's almost a GOMP space satellite, and the rest of it is all the different things that that we're going to show you in a minute. And the idea behind launching a satellite was, I mean, the whole thing is trying and bring some more innovation and accelerating the rate that we actually get to experiment in flight. Normally we can't experiment at all unless when things go wrong. With lots of constraints. So the idea was to try and allow experimentation in flight, which is what we're going to talk about soon, about how to be an experimenter and how to deploy open source software on this and see how it reacts in orbit. So there is a full set of equipment there. We have sensors, actuators, star tracker, magnetometers, GPS, reaction wheels, etc. So all that's there. There is open access to all the telemetry, and you can get that via something called MUST. And if you're an experimenter, you can just log into MUST and see all the telemetry as it goes in, and we accept telemetry requests. There's also high-speed communication, so we have X-band up to 50 megabits per second. I mean, we're not at 50 megabits per second yet, but we will get there. S-band communication. We have a laser receiver on board, a software-defined radio as well on board, a receiver. So in UHF band, it's like a spectrum analyzer in space. And perhaps the most interesting thing here is we're flying an 800 megahertz processor with a reconfigurable FPGA. Now, most command and control processors are not 800 megahertz. So this is they're more like 24 megahertz would be the standard ESA command and control processor. So this enables us to do things which you can't really do on the normal ESA space. So why is ESA? One thing, we already have many new things flying on this spacecraft embedded in the control. So we have many new communication protocols which are way ahead even of the missions that we're planning. Things like the file transfer or different types of command and control protocol or patents and new patents. We're trying these out, and we use these every day. The thing, this is difficult, doing new stuff, but we're using these every day, and so this is helping to smooth the path for the future for us. But on top of that, there's another interesting thing, and I think that's where open source software comes in. Because we're flying that high power performance control processor, we can also, we fly normal software, shall we say, like terrestrial software, but that way, not embedded stuff, Linux, Java, Python. And we actually use this to control the entire satellite, because from this place where this high performance control processor is, you can basically do everything, and perhaps even more than we can from the command and control processors. You can rotate the satellite, take pictures, classify them, compress them, communicate with the ground, etc., over the internet. So part of this whole adventure is trying to see how we can exploit all that processing power and open source software, etc., deploy it in space and see what a difference it makes to how you would control stuff compared to the traditional way, which is embedded software, very, very classic control systems, lots and lots of conservatism. And finally, we also have this powerful FPGA. So it's a very powerful FPGA, Cyclone 5, connected to that processor. And we believe this is going to change command and control of spacecraft, just like onboard software did. When I started working in command and control, it was basically lots of analog switches and relays. And already the deployment of onboard software, I mean, you guys can't remember this, but it changed everything. It was a revolution, being able to change things as the spacecraft mission went on. And we believe being able to change a firmware in space is also a revolution. And we're already seeing that in some of the things we've done on OPSAT. There's no way in the world you could do this on a normal spacecraft. And it's incredibly powerful. So what do we offer on OPSAT? So as well as being this for ESA, we are offering this also to the public. This is the first public satellite, shall we say, where the public are allowed to deploy their own software. So, and this is the point where the whole idea behind allowing the public, and by the public we mean everyone, but could be firms, could be institutes, but it can also be individual people. And we do it at no extra cost. So there's no extra cost until November 2021. Basically, you get to use this for free. No bureaucracy. You fill out a form. It takes 2 minutes, and from that moment on, you get access to the platform. You can see the technical documentation and the actual getting the software on board, especially if it's following standard practices. Is really, really easy. You get to do stuff, and you get the results. And we don't ask for anything. We don't ask that you have a paper or fill out any form or tell us even if it worked or not. This is the idea is that it's for you, and we are the facilitators of that. And we look after the risk of the spacecraft. So you don't have to worry about that. We're gonna look after the spacecraft itself, and you can deploy your software. And this is the idea. So the satellite can be reconfigured in many ways that are completely impossible. Like we can bypass CCSDS protocols on the communication, for instance. You can change the firmware, as we just said with the FPGA. You can reconfigure the entire processor. I mean, you can go down. You can just, in fact, it's even possible to get rid of Linux and start at bare metal. So. And also for the first time, you're also allowed to command and control the spacecraft over the internet. So we allow the ability, in fact, we did the first one on Friday, an external experimenter to command and control their experiment over the internet. And remember, the experiment can be really powerful, like rotating the spacecraft and stuff like this. And of course, there's an OPSAT community. I'm sure the guys will talk about it later, where we have lots of experiments already. We have 151. It's always increasing, and of course there's a community there where it's a good idea to synergize, exchange. Experiments can be built on top of each other. Now, the story so far is, because this is open source software, the first thing I have to say is SatNogs. So we thank you very much. So we start, although now the mission is doing really, really well in terms of we have a X-band and S-band and megabytes of telemetry going up and down. It wasn't like that at the start. We had a terrible time to start with. The first pass we took, we had no packets, no commanding. Yeah, for several months, we relied on UHF with a very bad link on our side, and a very bad, big thank you to SatNogs, which is an open source project. Because without us, I really think we couldn't run the mission. So yeah, thank you for saving our mission. Also, Linux, the power of Linux for me wasn't obvious until I saw all of my team basically using it in such powerful ways. I couldn't believe it. Yeah, so I mean, I'm sure they'll go on about, but I come from the old way of operating spacecraft, and seeing them use this, the power of Linux to make the thing efficient is quite amazing. And Python, we have Python on board, and managing the experiments is a completely different way of working with things, deploying Python packages and doing some amazing things. TensorLite, so again, I mean, George will talk about this, but I think it's one of my key experiences in this whole lot is watching somebody go from zero in a couple of days to actually deploy artificial intelligence on the satellite, and for it to be used a couple of days after that operationally. So the power of it is quite amazing. And finally, this could be only the beginning of open source software in space on OPSAT, because yeah, we're going to take this further and further, because I think it's the most promising route. And just to think, if anybody is looking for a challenge that would be instantly valuable to us on the mission, and of course we would recognize this because of that value, here's one. So what we have, our problem is that the ADCS controller, we have magnetorquers as actuators, and we have magnetometers, sun sensors, photodiodes as sensors, but we have up to now not being able to achieve nadir mode. So that means pointing the spacecraft at the ground to be able to take photos and things, etc. It's not as easy as it sounds. So it sounds really easy, and of course we have things deployed in terrestrial software which works perfectly okay, but it doesn't work in space because for any of you who've tried to do this, it's a different environment with different problems. But if anybody wants to take that up as a project, then I would 100% support them, and I would promise to deploy it on the spacecraft operationally if it worked. Okay, there you go. So this is my last slide, and just although this is not the best picture from OPSAT, I do like it the most, and here you can see the things that can be done. So this is a picture of Argentina, just over Argentina. You can see some fires and the smoke rising up into space, which yeah, it can all lead to all sorts of possibilities for doing stuff. And I terminate my presentation there. A big thank you to my team who are going to present now. They're the best engineers I ever met. So and it's all down to them. So thank you very much, and I hope it all goes well from now. Bye.
Thanks a lot, Dave. This is amazing, and thanks for highlighting all the things you relied on, and the team, of course. So next to speak, I think, is Tom, and you're going to go in more details. I'll make you presenter, Tom.
All right.
This closes your screen sharing, Dave. I hope that's okay. Okay, George, I got your message.
All right, can you hear and see me?
Yeah, I can hear, I see you. This is amazing. Great.
All right.
You're sharing your screen?
Yes, let's have a look. Share. All right, first try. Nice.
Perfect. Okay, the screen is yours. Go ahead.
All right, thank you. Yeah, thanks, Dave, for the introduction. So I'll now be more focusing on the actual details and how to get involved in OPSAT, what you can do, how you can do it, all sorts of stuff like that. So without further ado, let's jump into it. Wait, I have to click here. Okay. So I'll briefly show you our experimenter community and how to get involved. Dave already briefly introduced what the payloads in OPSAT, but I'll go into a little bit more of the detail on the specifications and what sort of results you can get there, as well as how we test and upload your code, but also how to communicate with your app in orbit, since, like Dave said, we had our first last Friday, which was quite successful. I'll talk a little bit about the operations, and also highlight amateur radio and OPSAT, just a slide or two. And then we will go to some live demonstrations. We have quite some things to show you, so hopefully it all goes well. We did have some issue with the fact that for our demos we needed the ESA VPN, and for some reason we can't join the conference when we're on the VPN. But so you might see some of us which are dual joined with some accounts. So hopefully that all goes well. So let's see, we'll do our best. And maybe if it even goes well with the time, we will have a live pass demonstration with the spacecraft. All right, I'm just gonna, because I'm also logged in here with two computers. Okay, so about our experimenter. So as Dave already said, so we have a very wide range. So we have startups, universities, even individual research groups, but even large corporations. So you see, for example, Airbus, CNES. We have a very, it varies greatly, and so do the subjects of the experiments themselves. Up until now, we've had 153 registrations, and the main interaction happens through our community platform. So let me just drop the link there. As you can see there from the distribution, it varies a lot. So a lot of the applications are on board with respect to image compression, housekeeping, telemetry, but also have some experiments using the software-defined radio, like you can see, some ADCS monitoring, a lot of scheduling and autonomy. So this is something that's actively worked on, as well as inside ESOC itself, for more smart scheduling, so to say. Like I said, so our community platform is like the central, the core of the OPSAT mission. I've just pasted the link in in the chat there. So what we're using it for. So first of all, like Dave said, you can get every spacecraft telemetry parameter that there is in near real time, and also export those parameters, look at command history. So that's one thing that this portal provides access to. But also, most importantly, live connection. So when we test your code, or you want to check your application, you can also connect to our testing infrastructure, which are a couple of flatsats, which I'll talk about in a minute. But also even connect to our mission control system and send and receive your data over the ground station link. So this is something that's very powerful. But also software submission. So all the code you write, you can submit. There's an automated packaging pipeline, which we'll also talk about in a minute, which basically packages your code and does checks on it to make sure that it's safe. And then we can deploy it on our flatsats. And if everyone's happy, we can deploy it in orbit and go from there. Also data dissemination. So if your experiment generates log files, images, IQ files, radio recordings, you name it, you generate it onboard the spacecraft, and we synchronize it with the platform there, and you can get your data via SFTP, all in a near real-time fashion. And also our experimenter support. So there's a lot of hardware, software documentation, news updates, forum, bug report, issue tracking, all the usual ecosystem that you need to manage a project that's complex as this one. So just a brief overview. I've pasted the link. Have a look. If you want to get involved, there's instructions on the homepage. So just shoot an email to Dave and me as well if you want to get involved, and that's the usual standard procedure. So more about the possibilities on OPSAT. So like Dave, you already showed you a nice image. More specifically, we have a resolution about 70 meters per pixel. Of course, a color camera with variable exposure range, and with a resolution of 2048 by 1944 pixels. So some more images there, just for reference, what you can do. We also have an advanced ADCS. This is not the ADCS that Dave mentioned we have problems with. This is sort of another standalone unit, which we allow the experimenters to have full control over, which also has a star tracker and reaction wheel. So this one does have the option that it can do quite precise attitude determination. Also, since it's a Cyclone 5 system on chip, there's also an FPGA section on the chip, which we allow the experimenters to synthesize your hardware on, IP cores, you name it, new telemetry framers, deframers. It can basically be anything. Also have an optical receiver on board, so the uplink rate here is rather limited. So the function of this optical receiver is not for super high gigabit data transfer rates, but it's merely to transfer either an encrypted key or other data sort of at a lower rate, but still in a reliable fashion. Also, we have a software-defined radio, the LMS 6002D from Microsystems, which in theory the front end does cover 300 megahertz and 3.8 gigahertz, but on OPSAT it's connected to a monopole antenna. So I would expect still decent results between 300 and 800 megahertz. So that's sort of like the active receiving range that we're looking at. Also an X-band transmitter, which we can directly interface to the FPGA, so through LVDS lines to either implement custom high rate file downlink or similar experiments. Finally, but last but not least, is the core of OPSAT itself. We call it the SEP. It's the Satellite Experimental Processing Platform. It's basically two Altera Cyclone 5 system on chip where we run on the ARM core embedded Linux with Python available, Java, C, C++. Anything you could run on ground, you could run there. So also some examples there. That's what okay, it works. That's what it looks like. Also, this bottom spectrogram here is when we recorded a UHF carrier that was uplinked and recorded basically on the spacecraft, and then downloaded it as a IQ file. And I believe this was analyzed using InSpectrum, which maybe some of you are familiar with. It's also on GitHub, so it's quite interesting there to see that working. So how we test and upload your code? So software on OPSAT is managed by OPKG. So any files or executables that we upload are always in the IPK package format. This makes it easy for us to essentially keep track of the file, so that we can just do issue install or remove and update. It's very simple from a management point of view. We have two testbeds available. So one is our FlatSat, which is a smaller version of the spacecraft, which only has the onboard computer and a couple of power distribution units. However, we also have a fully fledged engineering model, which you can see here, which has almost everything the spacecraft has except the solar arrays, the radio, a couple of radio modems, and also, I believe, what else doesn't it have? Yeah, of course, the S-band antennas, and so it's sort of a it's most of the things you would need to verify most of the experiments we come across. We often test online, so with experimenters in the loop. So I'll talk to it about the next slides. So they make a live connection, and this is transparent for them. So it would be as if they were connected to the real satellite. So this makes it easy on the experimenter side to basically prepare ground applications and stuff like that. So there's usually several iteration cycles until we're happy with the performance. We simulate some orbital scenarios and go from there. So that's sort of like the testing infrastructure that we're looking at. So how to communicate with your app in orbit? So there are several ways, essentially four. So one is via, so you can see here that's ground, that's space. You can do it via files, so file-based operations. Either it's a scheduled file or a file described which has some timestamps. It can be anything you want. You can define it yourself. And those are synchronized in a semi-near real-time fashion with your application on board. So there's a path convention, yeah, you can get your own files on board the spacecraft. A lot of our experimenters also use space packets. So if you know the CCSDS space packet protocol, it's a way to directly talk up to your application OPSAT, because we route the packet on the CAN bus, and you can receive it on your application on board. I'll show it in a second in more detail. You can also run a command shell to the satellite. So this is quite unique. So you can just on the lower level, it just uses again the space packet protocol, but the payload itself contains the Linux commands. And finally, last but not least, we have also an MO services pilot deployment. It's sort of like a higher level topology on top of the usual packet utilization standard, where it's sort of like a higher level. You can launch actions, you can monitor telemetry. It will Dominique and Lorenzo will address all about that. So I'm just going to quickly go over these points. So like I said, how to get files up to the satellite. We use, again, SFTP with our community platform as a front end. You can transfer files in your, every experimenter has a home folder, you transfer files, and then whenever they're synchronized with your application on board, you will get a report, and then you can go from there. We also use CFDP, so this is the CCSDS file delivery protocol, which is also the first in orbit used by ESA. So it's also something interesting there. If you generate any images, log files, you dump them in your own home folder, a to ground folder, and they get synchronized whenever we have acquisition of signal with the satellite, essentially. And then you can just pull them using SFTP. So from an experimenter point of view, there's also a lot of room for automation, since you can just use your own tools, so to speak. Using space packets, like I said, this is usually done via port forwarding. So you port forward again into our community platform, which is like our front end server, where you can then send and receive space packets. You have to adhere to your APID, because this is important, because this APID is used to route basically your packet onto the payload onboard computer on the spacecraft. And then all you have to do on board is connect your application to a TCP server, which sort of broadcasts all the frames, and then you just filter for your own telecommands and telemetry. So it's a very interesting way of provisioning the link to OPSAT. Like I said, command shell. So it's like you have your own user on the stack when we install your experiment, and you can run any Linux command that you wish under your own non-root user, of course, which is also a first for ESA. So this is sort of what it looks like. We have a component on ground which multiplexes all the telecommands, and when you send telecommand, it gets according to the APID, it knows that it's a space shell command, so it formats it, uplinks it to the satellite, and you directly receive standard out on your end. So you can run anything from a shell script to just Linux commands. So basically anything, or launch your application via that. You can choose. You're very free in that respect. Of course, limited to your own non-root user. And finally, the ML services. So this is also quite interesting approach, since you can essentially control your application via a web browser. What that means is you can launch actions. So it's like a normal telecommand stack. So you can define actions, you can launch them, you can monitor telemetry, aggregations in this case, and basically control your app from a browser, which is even more interesting. So like Dave said, over the internet. About operations, we use the SMILE app of ESOC. So we're the main user of this infrastructure. So SMILE stands for Special Mission Infrastructure Laboratory Environment. We also heavily use automation because the OPSAT passes, due to the sun-synchronous orbit that we're in, there's usually 2 passes before 6 o'clock in the morning, and then evening passes after 6 o'clock after 6 p.m. So there's never an overlap with working hours, really. So we usually automate everything and pre-program activities and monitor the system. So of course, most of the commissioning in the last months has been done remotely due to COVID constraints. That was also quite interesting experience, but now we're quite used to it and have adapted quite well to it. Also operates on 3 frequency bands. We have the 3.7 meter X-band tracking antenna for our nominal file operations, high-speed telemetry telecommand. And we also have UHF, which we also use from time to time. The downlink usually we keep active to increase our coverage, also, again, via SatNOX, which I get to now. So amateur radio and OPSAT. So in the beginning, before launch, we published the downlink specification, so the formatting, how to decode it, because OPSAT uses UHF amateur radio frequency. So also in collaboration with Chris Bridges, I think he's still in the loop, yes. So thanks also Chris there. So it was quite an interesting experience. We saw a lot of activity, so the outreach was quite amazing. So there was a lot of signal reports during the LEOP, also including the first beacon reports, also via SatNOX, and also individual signal reports. So this was amazing to see. We also presented the GNU radio conference. Let me just quickly provide you the links here. So that's from our GitHub page. And then there was this publication, which should have the presentation as well as the paper. Okay. Yeah, so via SatNOX, I think the numbers are already out of date, but there were already more than 630,000 UHF packets received, and in total 13,500 passes with OPSAT. So that's quite some amazing numbers there. And we also do have more UHF activities planned in the future with respect to the UHF downlink, where we might look into image dissemination or other interesting activities, sort of transmit encoded text, or we still have to figure it out. But if anyone has any ideas, then feel free to reach out and we'll see what we can do. But there's definitely possibilities there. Yeah, here again, you can see sort of the wide variety of activities that we had during the LEOP. So we had the FH Aachen tracking us via SatNOX. There was also the Dwingelo radio telescope, which I believe also was one of the first to decode one of the beacons in only a 2-degree elevation pass. But of course, that doesn't surprise you if you have such an installation. And of course, on Twitter, lots of activity with people using GR OPSAT to decode the first beacon. So that was very interesting. So ESA so we weren't the first to make contact. So we saw already before we made contact that the spacecraft was healthy and that beacons were being transmitted, indicating the antennas had deployed. So this was very valuable. So again, excellent job there. And now I will leave it to Dominique, Lorenzo, and George to slowly start moving to the demo. So like I said, we had some technical difficulties, but let's see what we can do. So with that, I would say thanks, and let's now move on to the more practical session. So I see that Dominique says, I think George is ready to roll. So let's see how that goes.
Yes, thank you, Tom. Thank you. George, I give you presenter rights. You can go on.
Hello, can you hear me now?
Yes, I can hear you. You were muted, right? That's
okay. Okay.
Good. So you're the presenter. You can share your screen. It's in the middle, bottom, middle. Perfect. You
Yep.
got it.
Okay.
Great.
So.
Nice.
See. Get started. So I believe we only have about 30 minutes until the pass. Correct me if I'm wrong, Tom. So I'm going to try and do this a bit quick so that we can have some time for Dominic to do his presentation as well. Okay, so Dave gave me a very nice introduction on how we ran AI on board the spacecraft. And I'll provide some specifics in terms of how we used open source technology to achieve this, notably with TensorFlow Lite, and how the use of open source technology and already all these available resources that we can run off the box allowed us to run this and get started in about a week's worth of work. Most of the work for this was actually spent watching YouTube videos on how to train a model. I was a complete beginner in machine learning, so it really shows you the flexibility and the power of the platform of allowing someone who's completely new in the field deploy and launch something that's become an operational tool for day-to-day use in a satellite. So let's get started. Just a bit of background on what the problem was. So we have some challenges with our attitude control. And as Dave mentioned, we don't always get nadir pointing. So when we took images, when we were acquiring images, we were getting a lot of bad images. So either they were pointing out into space, either they were too blurry, or either they just weren't interesting at all. For instance, overexposed. So while we're trying to figure out the solution to our nadir pointing issues, what we could at least do is filter out the bad images that we get. And I thought that this is really classic machine learning 101 case study of feeding an algorithm, a training algorithm, a set of bad images, a set of good images, producing a model and running it on board. So this is exactly what we did. We used TensorFlow Lite to train a model, and we compiled a inference program using the TensorFlow Lite C API, which runs really nicely on board the spacecraft. And then the application itself to acquire an image and to execute the image classification program is a Python app. That's it. So now we're only downlinking images of value, meaning that are labeled as nadir-ish Earth images, or if we want edge images of the Earth limb, they're quite nice. And the app was also designed to have designed with reusability in mind. We'd really like to see other experimenters use the image classification program. It's designed in a way that it can run any model that is of TensorFlow Lite format, so a TF-Lite model file. And you can configure the size of the image input that you want to feed it. So for instance, I used transfer learning, so I was constrained to a specific input size of the images, but that's configurable, and we can input any image size. The app itself supports a pipeline, the upcoming version at least, where we can chain different models. So if you have a model that produces an output, you can feed that output into another model and get another output from that. And the idea is that we want to be able to build a chain of models and start crowdsourcing best models from here and there into some processing pipeline. And the reason why I had really wanted to push to use something like TensorFlow Lite is I really wanted to attract people who operate in this field with these popular frameworks, to give them an opportunity to run models in space, in the space segment, even though they don't operate in the space sector. So here's a bit of an example of what I mean by chaining models. We get an image, we classify it as either good, bad, or an Earth image. And
If it's an Earth image, why not apply another model and classify it as either a cloudy or non-cloudy image? A very basic example, but you can see the flexibility and the power of chaining these models and crowdsourcing these models. Again, the idea is grab everything we already have from the artificial intelligence community and replace this whole deployment stack with OPSAT, giving OPSAT some certain accessibility to all of the talent that's already been developed in the AI sector, particularly in the open source community. Moving forward, we want to start building ML chains in our image classification pipeline on board. And we want to, resource permitting, and if we can get some help, see if we can get other inference models, other inference frameworks running on the satellite. It'd be great to get something like PyTorch or Caffe running on board and not just TensorFlow. So that would be a really great project for any experimenter interested in running machine learning algorithm in space to get into. So I can run a quick model on the FlatSat, or I can stop now and leave Dominic some time to do his presentation so that we have enough time for the pass. I would say the latter, because in the demo, you'll just see this terminal command of acquiring an image and successfully classifying it, which is not that very exciting, to be honest, but to see, but it's exciting per se, but visually not so much. But yeah, that's it. Unless you guys really want to see it running on the FlatSat, then I would say let's move on to Dominic. All right, so if you guys want the demo, then I have to switch users, meaning we'd have to switch presentation rights from George Prez to George Ops.
Okay, I'm switching the presenter now.
Yeah.
George. George Ops. Okay.
And
so,
please keep in mind that we're assuming that we can share a screen over VPN. It might not work.
Let's see where it goes.
Okay. Let's see.
So George Ops now is the presenter, no?
Yeah.
Okay.
All right. You can see my ops screen, right?
Yes. Yeah.
All right. Great.
OSMCF. Yep.
All right. Awesome. So let's not disconnect my other user because I'm relying on it for audio.
We won't.
All right. So this is we're in the Linux distribution payload processor, which is on ARM9. So this is why we're able to run cool stuff like Java, Python, and C and whatnot. And this is why we're able to run TensorFlow Lite on board as well. So this is the processor that's a payload that gives us the processing power to do so. So I'm in my experiment folder here, and essentially I just have this Python script that will trigger an image acquisition, and then put the image, resize the image as an input image for the image classification program, and then feed it into the image classification program, which uses TensorFlow Lite. So I'm just going to run it. I've disabled the image acquisition because this is the FlatSat, and this is the small FlatSat, and there's no camera on board. But I've prepared an Earth image here, which it should classify correctly as an Earth image. So let's see, Python 3, fire, there we go. So here we acquired an image. It's resizing it using these image processing libraries. It ran the image classification program, which again is a C program with TensorFlow Lite C API. These are the results of the prediction. So it's 90% certain that it's an Earth picture. It labeled the image as an Earth. And in our configuration file, we said, you know what, keep images that are labeled as Earth. So it's keeping it. We told it not to keep the raw images. So its raw image file format doesn't exist. And then it's moving it to our toGround folder. And then if I move to our toGround folder and do a list, I can see I have an Earth directory that was created. And when I look at my Earth directory, I got my Earth PNG that was acquired there. So imagine this app running on a loop as we're acquiring several images, one every 5 seconds or so. Every time we apply the classification program, and it sorts it in a subdirectories, whether it's Earth, bad, or edge. And if we don't want to keep the bad images, it doesn't even bother sorting those. It just disregards them. And yeah, that's it. It'd be interesting if people can figure out a model that runs faster or a model that does more classification, like within Earth images. Maybe we want to see novelty detection or cloud detection or land versus sea or whatnot.
Very nice, George. Is your code available or?
It is. I can share the link in the chat.
Great. Okay, what do you need next? Do you need somebody else to present, or you will?
So somebody else. It should be somebody else's turn. I think it's
Dominic. Maybe sending you a message.
Okay.
Dominic, you can take it. I will close your presentation and make him presenter, if you don't mind.
All right, go ahead.
All right, Dominic. We are back to this very creative page. Stand by. He's doing audio check. All right. This is a very nice application, George, by the way. Thanks for the link. Okay, Dominique, we see your screen. Thanks, Pradita. I was saying that we can't hear Dominic while I was muted. George, maybe while Dominic is phone. Okay.
Okay. I think you should be able to hear me now.
Yes.
Okay, sorry for the delay. I forgot I have to connect with microphone. All right then. So hello. I would like you to introduce you to experimental framework. This is this highest level application framework that we make available on board of OPSAT that Tom mentioned before. So yeah, let's get to it. Oh yeah, I should be able to also do this, maybe with some luck. Okay, hello. So just a few points I want to go over. So system overview, what is NanoSatemo framework? What do we provide as a software development kit? What do we provide as auxiliary tools? And then we switch over quickly to two demos. First, I'll demonstrate really quickly what can you do with what we provide, and then I will hand it over to Lorenzo, who will demonstrate a higher level end-to-end application supposed to perform camera acquisitions in organized manner. Okay, so system overview. This is OPSAT. similar diagram to what Tom already has presented, just different, differently organized. All of the gray boxes are hardware. Here are the two buses, CAN bus, SpaceWire. Recently, we started using SpaceWire. Still working that one out. And here's our two main pieces of software: Nanosat MO framework with libraries, supervisor, and applications that you can build, and payload drivers, which is just a set of hardware drivers that NMF talks to. So what NMF is really it's a framework allowing you to build applications without having to worry too much with interacting with the hardware. What driver do I load? What command do I send? Or I want to have a telecommand or parameter available to the ground. How do I do that? NMF makes it possible with just a few lines of code. Then on our ground segment, after the space link, we have data proxy. This is something you might hear about, but you won't see it yourself. This is internal part of our mission control system. It routes data across different paths. And then we have another NMF element, which is called ground MO proxy for experiments. This one ensures that any kind of services, it's a service-oriented architecture, by the way, any kind of services exposed on board, like telecommanding, so action service or parameter service, are available to the application on the ground, because the applications that are made in a manner that's not necessarily fully aware of the link. They shouldn't be necessarily aware of the link presence or not. So whenever you need your service to be present all the time, like your parameters or your telecommands history, you make something that's called proxy. And then this is where you are, the experimenter. So you can interact with this software stack in different manners. So first, you can just use a web browser and use the top-level interface that we provide, which is lightweight web-based MCS. You could skip that. You could make a custom MO mission operation services or NMF-based ground application, which still uses this proxying facility. Or you can say, okay, I don't care about any of that. I just create my own ground application, which may or may not be MO based, may or may not speak NMF, NMF understandable interfaces. You could just connect directly here and send space packets via a dedicated TCP port. Okay, moving on. So what do we provide? We provide monitoring control. There is a payloads abstraction layer, which is really a hardware abstraction layer. So instead of having to do something with IMS 100 image sensor, you just use camera service. You say take picture. NMF supervises applications for a management component called NMF supervisor. We use this one extensively in operations. It's our central point, which starts and stops all the applications, whether they may be NMF applications or not. There are some basic signals that it handles for the platform. So the OPSAT payload processing platform needs to do a few things, like send a heartbeat to our onboard computer. A supervisor takes care of that for you. We do perform the space-to-ground replication via ground MO proxy. There is a whole concept of data model, which is called COM archive. It stores all the telecommands history on the telemetry history and the definitions. This is replicated across space-to-ground. It's a little bit problematic component, but we'll figure it out right now. And this replication provides us offline mirroring of the data on the ground. Now, the space application stack looks like this. We have satellite platform at the bottom and satellite bus. So you can see all the payloads here, all the interfaces that we use. So there is our NMF layers, which is payload abstraction layer. Those there is extra abstraction within NMF, which is called adapters. So in theory and in practice, this abstraction layer is platform agnostic, which means that we can run it on OPSAT, but we can also run it on any mission. In this case, it's either OPSAT or a simulation mission that you can run on your own computer. Thank you, Red. So we also have MNC services implementation with an NMF core, and there's those generic composites that you can infer, and there's application, which is your code. Service APIs, they are available. Okay, right now they are on my GitHub, but you can preview them all in a web browser and see what APIs we expose via MO services. Now, what do we provide in simulators? We simulate core OPSAT payloads, GPS, IADCS, and camera. We allow executing simulation scenarios, time control, visualization, interface, Celestia. Okay, this is work in progress. Any help on that would be very helpful, very appreciated. Portable implementation, which means that it works cross-platform really on Windows, Linux. It's Java-based. We also support since some time ago hybrid mode, which means that we can run simulator actually on board of our satellite or on board of our engineering model and payload some of the service and simulate some of the platforms services like GPS or navigation, because of course when you are in a stationary satellite, the GPS it's not moving, so it's not that useful. Okay. Thank you, Juan. There's consumer test tool that you can use. It's sort of a lower level tool that you can use quickly to test your application, also to interact with supervisor, which operationally you cannot do. And there's this lightweight mission control system, which is really a web interface that we host. We also provide it to you as Docker. So while all of the NMF, or I would say 99% is open source, lightweight mission control system unfortunately is not, although it is freely available to all the experimenters who send me an email that, well, read a license and say I accept it, and then you get the binaries, a set of Docker images. Yeah, you can. You should be able to demonstrate it in a second. Okay, so NMF in a production-like connectivity is this is how it works. This is how it works on an actual satellite. This here is broken by a space link, of course, and you can also replicate it on your own computer. It's just a little bit more work. Normally, you can just bypass this component altogether, connect directly to your NMF application, because, of course, this proxying is supposed to be transparent. So demos. I'll just very quickly run over my demo. Do you guys mind if we actually run a little bit over? If Tom wants to demonstrate the pass, then I'll say I do a quick demo, then we jump to the pass, and then I would say close to the end of the pass, maybe Lorenzo can jump in with the second demo of NMF.
Why not? Yeah, it's good. So if we can catch the pass, it's nice.
Okay.
Less than 7 minutes now.
Okay. So just jumping quickly to the NMF code. This is what I have in NetBeans right now. So what I can demonstrate to you is starting supervisor and perhaps showing some basic interaction with it. Debug mode is not necessary. I just discovered some compatibility bug with Windows, so I won't be able to start an application, I believe, but we'll manage. So this is the supervisor that just started. There's this tool that I mentioned, which is consumer test tool. you can use it yourself. It's part of NMF. It's part of NMS SDK, and you can actually display quite a bit of information about the supervisor already, and or any application that you connect to. Yeah, but what I wanted to show is actually this higher level tool. Let's see if this works out. So you get it as a set of Docker images. This is all described on this website. If you follow the news about lightweight MCS and you accept it, you get access to this. You download Docker image, you spawn the Docker image, and then you should be able to use this. So let's see if I made enough of sacrifices to the demo gods. Fetch the provider, connect. So since I wasn't able to quickly start application for this demo because of this compatibility bug that I mentioned, I just extended NMF supervisor quickly via. Normally, it's not supposed to be processing any telemetry or any platform telemetry. It's just a bridge for applications to do this, but there's nothing stopping supervisor from acting as an application itself. So what I did is in this basic adapter of supervisor, I added a few things like attitude quaternion. Here I added some commands like sun pointing, nadir pointing, unset attitude, and to expose them on the space to ground monitoring control interface, I had to annotate them with this Java annotation. So it's a parameter here, and here it's an action. Now I already connected to the supervisor. I can go to parameter browser, and those Java variables I just created are indeed available here. I should be able to show it on a graphical display, and you can see, never mind the error messages, that it's being plotted in real time. What we can also do is go to manual stack, quickly attempt at least to switch it to sun pointing, maybe then make a stack to unset attitude, and perhaps switch it to nadir pointing for, let's say, 0 hours, 1 minute, 0 seconds. Apply, arm and go. Let's see if we see any change on our quaternions. Might not be obvious, or maybe, let's see. Not sure if we have time for that, but I guess if I now unset attitude and perhaps switch to nadir pointing.
I don't know how long you need to switch to Tom, but your 3 minutes.
Thank you.
To impact.
Yeah, perfect. We'll switch over shortly. This is the last point of my presentation. Oh yeah, so here's the manual stack. You can see the action history. So all of them, they were successfully released, accepted, and completed on board. In this case, by supervisor. In your case, that would be by your application. Yeah. Well, we don't see much of attitude change. There is actually non-discrete slew implemented in the simulator, so I don't expect it to be immediately visible. Okay, this concludes my part of presentation. I suggest we quickly switch over to Tom for a pass.
Very nice.
And then back to Lorenzo to demonstrate the camera application.
Very good. Tom, this is to you.
Okay, can you hear me? Oh wait, I'm having some feedback.
We can hear you. We hear the feedback a bit.
Okay. Let's mute this one.
It's better now, anyway.
Okay.
Tom, I'm going to use this to communicate with you as well.
Okay. I think you can all see my screen now, right?
Yes.
Okay, so we're just waiting for our antenna to start tracking. So this is azimuth and elevation. So we're at 1 degree now. So this is for our S-band antenna, and then for UHF we have our connections here. Okay, so we're connected via tunnel to our UHF ground station in Austria, so no data yet. So let's switch over to prime chain. So this is this this data proxy which Dominic was referring to. So we're connected to our Cortex, which is our ground station. We're connected up to the MCS. Okay, all looks good. This is our automation system. So all procedures are essentially loaded as XML files. And there were already all the telecommands sent. So we're now waiting for a response for the spacecraft to do the time-tech Q check to basically resend the schedule. So we're just waiting for AOS now. So let's see.
Your elevation is at 3 degrees.
Okay, so we see a weak signal on the downlink. Okay. Stand by for telemetry, and we have telemetry. So there's idle frames. Let's just filter for 8 bits. And now see some housekeeping data. Okay.
Your carrier is enabled.
Okay, yeah. So we're getting data here. So we're seeing anything from pseudo beacons to fault detection, isolation, and recovery, to down to quaternion. So let's just check here. Our onboard software mode is operational. Everything looks okay. We just saw a response to a watchdog reset, I think. Let's switch over back to Mattis. We're basically now waiting for our onboard receiver to get a lock. So you'll see here this green TM flow. So we have S-band telemetry coming down, but we don't yet have a lock on the onboard receiver. So there's no telecommands yet that are arriving. So we have to wait for the signal strength to increase, and we should have a bit locked shortly. So signal is down.
Tom, you have an IPK in the IPK folder. Also, a last chunk of a PNG that's set to downlink.
Okay, so we should see that. Okay. Now just a waiting game. So we're at 11 degrees elevation. Okay.
And Tom, I'll wait on your call to send the spatial command for the PNG split for the next image.
Yeah, okay, stand by, please. Yeah, we just have to wait for the onboard receiver to get a lock now, so it's a waiting game. Okay, signal strength is increasing. We should soon see TC link go green if everything's okay. We're getting quite some CRC errors on the downlink, but that's okay since those are filtered out. So let's just wait a little bit now.
Tom, can you have client 4 on the side?
Yes, stand by.
In case there's time to run the spatial, it might be interesting to watch.
Okay. Yeah, I mean, okay, I see. Yeah, okay, I'll just keep that ready. I'm just waiting, I'm still waiting for the signal strength to go up. Just keep it here. Okay, it's increasing, so we should soon have onboard lock. Let's stand by.
Tom, that's lock. It just says it wrong. You can go with it.
All right, yeah, we have one TCV. So now there should be schedule being resent. Okay, and we're receiving responses from the spacecraft. Okay, good. So all these S's here, that's basically activity tracking. So for example, this first A here, it means it's accepted on the spacecraft. The C means that it's completed. So we can basically track the execution status of a telecommand all the way from releasing the telecommand to acceptance on the spacecraft to execution on the spacecraft, and trace this all the way back down to see if everything completed fine. So we have one more command to send, and I think we're all fine. Okay, so as you can see, I'm not really doing anything. I'm just looking how everything is doing, and we're already downloading some files. So we should see here on MCA the CFDP frames being received. Yes, and we're seeing them. Okay. So it's basically now, I believe, George, it's an image coming down, right? It's
Exactly. It's the last chunk of a PNG image.
okay. Okay, I see. So let's switch over to Mat A. Okay, yeah, and here we see onboard telemetry, which was compressed and stored, being downloaded now. Like Dominic said, we're now also working on SpaceWire, which should now allow us to fully saturate our one megabit downlink rate. So we're now not quite at that stage yet. We still need to integrate operationally, but we should then also be able to use X-band and go to 6 megabits effective file transfer rate. So this would be very interesting to see.
Tom, this is what do we see right now? Those are logs of your spacecraft.
Yes, so this is a log from the automation system. It's reporting the completion of a file download. So you can see here from the ground station, we're receiving all these packets here with a certain APIT. So this is APIT 124. And you see here that this daemon reports a connection here. So it's being routed to an application which sort of assembles this file. So if you look at this file, it's just binary chunks of the image file, either compressed or uncompressed. It really depends. So actually, we could have a look at what's on board. Should maybe still be in the log, but let's check. Complicated enough doing this live, let alone over. Okay, there we go. So those are all the files on board. So we basically dump the directory listing with all the checksums, the file path, and then the size. So that's the response basically from the spacecraft, and then we iterate over those files and we trigger a downlink for each one of them individually. So that's what you're seeing here. So we have, I think we're almost.
You have about 1 minute left.
Mm-hmm.
I think there's no BitLock anymore.
We lost the PC link. Okay, yeah, we lost it. Okay.
So just for your information on a technical level, the way it works is we get a stream of idle frames all the time from the S-band transceiver. And at the end of each frame, there is so-called CLCW, commanding link control word, I think it's. And in that CLCW, you actually get a feedback from the transceiver, whether we get a RF lock and then a bit lock and a frame lock.
I can bring up the.
Thank you, Ian.
It's called. Oh, there we go. CLCW. Right? Okay, I got it. Yeah, here we go. So yeah.
Then I suggest we close it out whenever and go back to Lorenzo for a final check.
Yeah, I think. Unless, George, was there anything else you wanted to? I mean, the pass already over, so all the other will have to be rescheduled or.
No, it's good. It's okay. There was no opportunity for the IPK to complicate.
Do you want to assemble the image that we download to feel like, or shall we let Lorenzo do?
I'll do it, and I'll share it after Lorenzo's talk.
Okay. Perfect. Yeah.
All right.
Should I make Lorenzo?
Please.
Yeah, I have to share my screen.
Perfect. You're in. Remind you, we're soon finishing the workshop, but we want to see the picture.
Okay.
Cool.
I'm starting with a much simple demonstration, the camera acquisition system, which provides a full end-to-end experiment, which includes a user interface, a ground application, and a space application. With the objective of the system is basically to schedule the activity for taking a photo or a defined ground target from the spacecraft. The system is constituted by 3 different applications and demonstrates the communication between the ground and the spacecraft, the interface with the onboard camera, the controlling of the spacecraft attitude, and in the end, the prediction of the orbital position of the spacecraft. The camera acquisition system is tasked with planning and scheduling of photographs, implying a minimal intervention of the user throughout basically a high level of automation. The user is provided with a few crucial information needed, which results basically in an easy-to-use system. The system can be conceptually divided into, sorry for the, give me a second, can be conceptually divided in two segments, which in this example will be resident on space and on ground. The first, very simply, is the space app, which is resident on board the spacecraft and is responsible for telling the spacecraft when and where to orient in order to take the photo. On the ground part, the ground application calculates the time slots of the satellite passes over the target location and fulfills additional constraints. While the ground application also prevents multiple photographs to be scheduled at the same time. And finally, dispatches the photograph commands to the spacecraft and save the progress information received from the spacecraft. Last but not least, there is the Django application, which provides the user with the web server interface for the correct for interfacing with the ground application, which can be done by remote, as you can see. And it also displays the ground track of the satellites and provides the tracking information for previous photograph requests. The operation procedure of the entire system is shown here, and I will quickly, for example, it. The operation procedure starts with the user inserting the desired target information through the web server interface handled by the Django application, which are then transmitted to the ground application, and the ground application then calculates the time slots available for the photo using the current two line elements of the satellite by propagating the orbit either until the entered conditions are met or until a maximum time slot, which by default is set to a year in the future. The time slots are then sent back on the user interface. And at this point, the user can acknowledge for a specific time slot of the proposed ones. The Django application will send the request back to the app, which is responsible then for communicating the same request to the space application. The space app then starts a countdown from the present time of the request to the targeted time. Eventually changes the spacecraft pointing mode in order to point to the camera to the ground target, and finally takes and saves the onboard photo. And now I will quickly give you a demonstration using a simulator. As you can see, the user interface that you have here as first shows the current ground track of the spacecraft. On the right side here, we see there is a set of parameters we can insert. These are the latitude of the ground target to be photographed by a spacecraft, the longitude of the ground target, the maximum angle of inclination of the line of sight between the spacecraft and the target, and it is also possible to choose whether take the photo at daytime, at nighttime, or at any time, like in this case we will do. When proceeding with the request of the access information, the Django application communicates the input, as I said, the input parameters we selected to the ground application, and which in turn gives us back a list of accessibility time slots of the spacecraft over the ground target. These time slots are ordered, as you can see, from the closest to the latest. We can select one from the list. And by selecting one slot and proceeding with the confirmation of the scheduling, the ground app saves the request and assigns an identifier to the operation, which can be used to retrieve the operation status. Here is 17. So if we type 17 here, we see that our request is waiting for the uplink, because this is just a demonstration. But after having saved the request, the ground application sends it to the space app, which as a response should have started a timer here, which tells us, as I already said, that at the end of that timer, the satellite will orient to the ground target coordinates and take the photo. Of course, in a real operation environment, this will happen. And this is simply the end of the presentation. And thank you for your attention.
Thank you.
Okay.
Of course, at the end, the picture is stored by the application, and then you end up with it getting downlinked by the flight control team.
Yeah, exactly. The application itself is not responsible for downloading and showing to the user the photograph, but this is of course an open point which can be added as a feature to the application.
Do you still have the application at hand? Maybe you could.
Sorry.
Never mind. Yeah, I was wondering if you could show maybe a polar region with some of the also with a larger angle.
As you can see, since the OPSAT is on a polar orbit, the greater is the angle, is the latitude. The more accesses we will have, the access will be closest to the present time. Indeed, as we can see here, is on the 14th of January. Maybe if we go down to 0 to the and we do it again, so no possible way with this times a year. We see that what happens is that the accessibility is so low that not even in a year time it is. I don't know how accurate it is.
All right, Lorenzo, Dominic, George, Dave, Tom.
Thank you.
Yep.
Closing remarks.
Yeah, I'll have an image in a minute or so.
All right. Maybe we can stop it up. Good. But thanks a lot. All those declaps. It's like we have a lag in time zones, so the claps, they come one after the other. All right. Arto, could you share the slides? Perfect. Great. So we're wrapping up. So that was a day where we had day 2. We had an amazing first track with TLEs and OMMs on room 1, Polaris and machine learning for space ops, Orbit M for LEO orbit maintenance in Python, dual random CubeSat flight computers using Raspberry Pi, and LSTN with Nico showing how they developed the library Space Technology Network. Then on room 2, we had Metasat, so metadata for small sat missions, nanospace. We had then an open source tool for to help concurrent engineering teaming in CubeSat preliminary design, an open source onboard computer platform for CubeSats, and Doppler-based orbit determination with optimization. We also had the Cubic Twins presentation from Elias, showing the details of the mission. That was nice. We had lightning talks. Only one didn't show up about the detecting small space debris. Too bad. But we had an amazing set of presentation, Phoenix from Damian on Federation, a portable software-defined ground station, so in the backpack, thanks to Baris, the open source space podcast with Jan Peter, and I hope you filled up his survey. Mechanical design software for space applications using open source software with Mantos. Nice comparison over there. And picofluid dynamic actuator in CubeSats that plan to be open source at some point. So looking forward for that. And then we had amazing sessions here that we just finished the OPSAT in this room, showing us how they write, load, and install and execute code on OPSAT. We had the chance to have the pass, so we even saw the things coming in, and we could track and monitor what was happening thanks to Tom showing all the screens. And then on the other side, we had Arthur presenting RESTful data storage and visualization. Maybe Arthur, you can summarize what was your sensations over there. Of course, amazing.
Well, we did. We went through the tutorial, and that was quite fun.
Yeah, nice. I was trying to install TensorFlow Lite to get me running on preparing an application for OPSAT, and I think the whole Polaris team is on it, actually. So this is the wrap-up. This was today. I think we can just applaud everybody. Thank you very much. It was amazing. Woo! So maybe you want to continue on the slides, Arthur.
I linked to the image. There you go.
Okay.
Great.
Yeah. So this all started 2017 over a cup of coffee. The idea was this open source CubeSat workshop, and here are the pictures from that time. The first one was at ESOC in Darmstadt, Germany, and then after that. We hosted it in Spain.
You have to activate the multi-user clicking here.
Yeah. So you can. Right. That's a good idea. You can draw a circle where you find yourself, or put your mouse on it. It's good enough. So we see. And if you were not there, maybe you go somewhere here in the corner.
Exactly like that.
Very good. And then last year. We were in the conservatorium in Athens.
You have to
activate for every time. Okay.
Sorry about that.
Yeah, right. Very good.
There was and Tom is appearing on every picture. This is really nice.
Take a seat.
I see you, Arthur. Yeah. In the middle, orange.
What? Okay. And yeah, this year we used the location. We were actually at your home worldwide, and with some fantastic graffiti taking place during the sessions. I mean, this is something we could not have done with a physical event, because the cleanup would just be terrible. But here, this is all possible. Great. So yeah, identify yourself with your...
We can turn our cameras on and try to take a screenshot. That would be the closest thing to a group picture.
Right? Actually, you read behind of the the slide. Juan, this is amazing. So, group picture. So everybody turn on your camera. And hopefully 42 people, that's the right number.
So you can minimize the presentation. If you click on this hide presentation button, and then you see all the webcams. So we're waiting a bit. Everyone hopefully has a webcam, and let's see at what point the server crashes, and then we take a group picture.
It's actually working pretty well. Impressive.
This is the best video conference I've been in all the year. You know, nothing broke. Everybody had good audio, good connection. Amazing.
Yeah. After taking the photo, I will transfer this with KGSTV over QO100 in 5 minutes.
Okay.
It's waiting there.
Very good.
Did somebody actually take a screenshot? Ah, Freddy, there you are.
I'm taking several screenshots, I think.
Several, okay.
Oh,
Wait, there's some more people joining.
Good. I thought it was stuck on 25 or.
Yeah, it was stuck.
Yeah, great.
So, okay, smile. No, there's more. Wait.
It's like, you know, you're entering a small room and everybody's like pushing each other. Yeah. You see you guys. I'm Fred. Nice to meet you.
I guess there's more.
Okay, everything on YouTube.
Exactly. All right.
Good.
Hey, Vladimir. Good.
Vasilis also joined, and we have Jose Manuel.
And also, please screenshot on the server resources now and CPU usage.
Yeah, it'd be nice.
We tested with robots. Konstantina, hello. We tested with robots before, but the robots starting to drop out after 25 robots. So yeah.
Red, come back.
Yeah, I'm still here.
Very good.
35 cameras, pretty cool.
I think we should send this then to a Big Blue Button. They will be so happy.
Yeah.
Red, come back. Where are you?
I don't know what's happening. Give me a second.
Red is grabbing his son.
Yeah, okay. I'm here.
Okay, good. And now smile.
Jeez,
Diego, your camera froze. No, it was. All right.
Yeah, Alex, nice suit. Very well done.
Good work, everyone.
We're glad. Thank you.
All right. Excellent.
Very cool.
So you can
presentation with the bottom left, bottom right. Yeah. Ooh.
So the other interesting and cool aspect of doing this this year was that. So we choose the time from central. So my local time is from 2 to 6. So that made it possible to cover a lot of time zones. In fact, we had people from Australia all over to the West Coast, I guess. At least everyone had a more or less convenient time to join. And this, I think, is really only possible online. Unless you do all this traveling. So that was really nice. Yeah, there's one aspect I like to mention here is diversity that I don't see that much in the audience this year, and I would like that we focus a bit on making the community as diverse as to reflect more what actually the world looks like, and in order to get a lot of new inputs and have many different opinions here represented. And well, diversity is something that you cannot, it's not enough to just say everyone is welcome to join. You have to actively pursue this. And this would be my message to all of you, to kind of look a bit into how to get other people who are, to take part in this workshop. That would be great.
Yeah. And I think this is not just us, this is also you, invite the people, try to be diverse in your invitations as well. And then motivate people also, because, lack of diversity also comes from, there's feeling of a barrier somehow. we're open, we're inclusive, no matter where you are from Earth, or even if you're not from Earth. So.
Okay, what was the next slide? Yeah, your the highlights, takeaways that you had from this workshop.
This window is very small for me now.
Is it?
Yeah, for me too.
Yeah. Okay.
No, you have to drag the. Yeah.
Yeah.
Red, you can drag it.
No. Okay. Stop sharing webcam. You have to stop sharing webcams, I think, for a bit. This is a feature. LF, could you turn off your webcam? Great. And now I think you can come back if you want. Yeah, this looks good.
Oh, come on.
We did this big line.
Who made the line?
There's a lot of things. Cubic platform. OPSAT. 3 times. OPSAT possibilities. Oh, we have the cleaners passing by. Good. Open source from day one. Yeah. Another highlight is people actually using people's open source projects. That's awesome goal. The whiteboard is the highlight. Well, thanks. The content of the workshop. I mean, that's you guys. So thanks a lot for everyone. BBB, I think we have to shoot out for them on Twitter. Say hi. Say thank you. This is not even the last version of BBB, so. Icon lights.
Someone vandalized the heading.
Yeah. Transformation, you can, you can modify the source code of the slide. Very good. All right. Docs, of course, docs. First one for a cubesat, machine learning on OPSAT. This is amazing. Having Dave saying thank you for open source projects, that was really nice. Thank you, Dave. Thanks a lot. I think I can say that on behalf of everyone. My background, this is a Gaia, so actually the credits are here, yeah, somewhere. Very cool. So how about we go to next? Their next slide, Arthur. Actions, yes. So please here list in a very clean way. We trust you. Key actions you would take. Like I say, it's like your 2021 resolutions or something like this. Something you would like to do and you plan to do. Open source air bearing test bed. I think I've seen that on Diego's video. Or was it different?
Yeah, this was one of the things that was pretty surprising, and yeah, we'll definitely work on making that available. I didn't know people wanted that, so yeah, it's
yeah, everything that is like facilities to test. I think that's.
And you can use it with any compressor you have. It doesn't have to be like a powerful compressor. We're using like a airbrush compressor, and it makes for really cool testing data. So yeah, definitely we'll work on that.
Cool, thank you. There's now some awesome list, awesome space I see on GitHub that just shared. So you want to share that? Very cool. Great, and I think I could say, like, if you want to speak about your project before the next open source CubeSat workshop, I think Jan Peter would be more than glad to have you on the podcast. So reach out to him if you want to do those kind of things. Oh, Fernando, you did the same. And now it's about to open the design. Very cool. All right, let's take a picture. Take a picture of that slide. And we will see you soon in 2021. I already don't know how to close this. I mean, I would love to stay here, and but this is goodbye. This is actually see you. See you next time. And I imagine, you know,
Brett,
yeah.
Before you cut, any plans for 2021?
So yeah, that's what I was going to bring up. So this year, the initial plan was to be at the Center of Astrophysics, you know, with Nico, Daina, you know, Kate and Dan last year presented, and we should have been there. It would have been the East Coast. Would have offered our American friends the opportunity to come easily. And so we'd love to do that still. So we have to see with them if that's still an open proposition. I don't know, Pieros, maybe you interact with them on Metasat quite regularly. So I don't know if Nico is here or anyone from the center.
I think it's still on the table, and yeah, we'll have to see, you know, how 2021 works out in terms of COVID and traveling. Hopefully, that's not going to be an issue, right? But yeah, like.
Yeah, they had the room. They went through the training somehow. We did this kind of training, so I think it should be all right to go over there. But if you have any other suggestion, please forward it to us. We'll check it out. That said, also, like, we meet once a year, but maybe we could meet lighter. You know, some kind of a space barbecue before the workshop somehow. Something lighter. We just. Hang out around, maybe just lighting talks or sharing tutorials. The open source CubeSat week, you know, something like that. You know, one hour every morning. Why not?
In that case, we can offer Greece as an option to have a nice open source space vacation.
Yeah, that could be just a remote even. You know, it's. Thanks, Philip. Yeah, the open source CubeSat workshop morning show.
Yeah, like
the daily show.
Something like Red and Pieros in the morning, or we have to.
We need a jingle for that.
Why not? Let's try that. Yeah, and Jan Peter, maybe you could animate these kind of things with the experience you gain with the podcast. I don't know. So open for that. I think ready to pass the message on if you want to do it, if you want to organize it yourself, and we just help you do that. That's just perfect. Yeah. We tried the breakout rooms. I won't try that again because it's a bit frustrating. It takes some time to join the people. And but thank you, everybody. Thank you very much for your participation. Thank you for answering the short notice. I think that was the fastest cool paper ever, fastest review ever, and you made everything clear. That was really cool. We had a lot of people. You said it with the time zone, Arthur. As, I mean, from the US to from Vancouver to Australia, so that was quite nice. And yeah, awesome open space. There's an awesome list that Pierre just shared on the link on the chat.
I just forked the existing awesome space, and we do some cleanup in terms of open source and keep just the open source license ones. And we should be adding many different projects. Many of them were presented here. So yeah.
Super cool. So guys, turn on your mic. The workshop is finished. Thank you again, and you can stay here around a bit. I think after we can leave the server turn on, and actually you can.
We can stop the recording though. Then
we can stop the recording.
You're free to do what you want.
and
probably the streaming too, right?
So you can see the. If you enlarge my webcam, you can see the server load.
So let's try again to crash the server by everyone going on with the webcam, and
and I will try something
while drawing on the screen.
By the way, Keros, I would like to thank you that my interaction with this Satnox thing was you. I think it was 3-4 years ago on you were looking for someone to develop the Satnox to give G-Predict integration. And I was the volunteer that time.
Wow! Yes, you were. I now remember it. Wow, that's back in the day.
Always
pretty cool.
You're doing great things. Thank you.
You too, and thanks for sharing your projects, and I'm looking forward to contribute to them. Actually, I would like to build a portable station for Q100. And by the way, the image just got back, right? Like I don't know you've seen that; it's already decoded.
Yeah, thank you.
Goodbye.
Bye.
Bye. Bye-bye.
Bye.
That means the recording is finished. Now we are off tape.
Woohoo!
Bye. Okay.